Good morning, everybody. Welcome to the workshop on spatial data analysis with PySAL. We're thrilled to have everybody here, and this is quite a new experience for us. We've done SciPy workshops before in person, and they've been wonderful. This is a new way to do it. My name is Sergio Ray. I'm director of the Center for Geospatial Sciences at the University of California, Riverside, and co-founder of the Python Spatial Analysis Library. Today I'll be co-presenting with my colleague, Knaap. I'll let Eli introduce himself.
Hi, folks. I go by Eli. I'm Eli Knaap. I'm the associate director at the Center for Geospatial Sciences at UCR. I have a PhD in urban studies and planning from the University of Maryland, and I've been at UCR now for about 3 years. I'm a core developer of PySAL, and I especially contribute to packages like segregation and Tobler, one of which we'll see today. As Serge mentioned, this is a new experience, being all online, so I hope you bear with us. So far, the tutorial session, or the setup session, I think, went relatively smoothly, so let's hope we continue that success here.
Okay, before we share screen, for those of you who weren't part of this setup session, if you're able to install things on your own machine with the instructions on the repository for the session, fantastic. If not, there's a binder link on the website for the GitHub repository for the session, and that would allow you to play along live without having to install anything. And then later on, if you want to, you can, of course, install things when you have more time. So don't feel like you're excluded if you couldn't get things set up. Please use the binder link. The format is that we're going to split the workshop in two parts. I will cover the first part, and then Eli will cover the second part. So who's ever not presenting will be available to handle questions. So please ask questions as we go along. Let us know if the pace is too fast, too slow. We don't want to lose anybody. And let's see, I think logistically, those are the key points, right? In previous examples of giving this workshop at SciPy, the questions have been fantastic, and they usually bring a lot to the experience for everybody. So please, we encourage you to ask questions. We also will have some exercises peppered throughout the notebooks that will give you a chance to interact with the material and expand your skill sets.
Because we have this sort of team format, while one of us is talking, please feel free to lob questions at the other person. When you do so, you can either use the chat here in this window or the ask a question interface, but it's useful for us if you limit the conversation to this Crowdcast platform and not in Slack, because it's difficult to switch modes. So ask lots of questions, but please do it from within here.
Okay, then I'm going to start and I'll share my screen. So I'll take over. Hopefully this goes smoothly. Here we go. Okay.
You can get rid of me. Get rid of me now if you want.
Okay. So is everybody? Eli, let me know. Can you see the PySAL homepage?
Yes, we can.
Okay. So to orient things for people who are new to spatial analysis in Python and maybe don't know what PySAL is, it's important to give everybody some background. So PySAL is an old library. It's been around since about 2007. It was a collaborative effort between myself and Luke Gansland, who's at the University of Chicago. We benefited from stumbling into the Python world early on in my research career, and I felt that it was really empowering. But at the time, This is the late 1990s, early 2000s. There was really nothing in the Python scientific stack for doing GIS, Geographic Information Systems and Science, or spatial analysis. There was nothing. Our own research interests were in the area of spatial statistics, spatial econometrics, spatial optimization, and visualization, primarily focusing on the social sciences, economics, sociology, political science, urban planning, and related disciplines, epidemiology. But at the time, there was nothing in the Python stack for geospatial analysis. Things like GeoPandas didn't exist back then. Things like Fiona, they weren't around. So we had to roll our own in terms of building shapefile readers just to get to the part that we're generally interested in, and that is developing new methods for testing for spatial clustering, new methods for estimating regression models on spatially referenced data. So it was pretty rough going at early days. Since then, things have exploded in Python for geospatial. So the spatial stack of libraries and packages that we can now rely on are fantastic. So we work very closely with the GeoPandas project because they're facilitating the processing of geospatial data in very efficient and scalable ways. And so that allows us, the PySAL team, to focus more on the areas where our research interests are aligned, and that is developing advanced spatial analytics. So that's what PySAL is about. It's organized primarily for vector-based geospatial data, and it has 4 layers, if you will, that we'll be exploring most of them today in the workshop. So at its core, we have functionality to read different types of spatial data formats, and then develop what are known as spatial weights matrices that we'll explore, that express potential relationships between your observations. The Explorer module or layer of the library has these methods for testing for hotspots. So right now, there's a huge amount of interest in detecting upticks in COVID, spatially explicit detection of hotspots, and PySAL is getting used very heavily for those kinds of research questions. Doing spatial analysis on networks, where you have, say, a road network, certain types of phenomena are constrained to networks. So we have facilities to test for clustering on planar networks, excuse me. Then the modeling layer, it has methods for estimating econometric models. When you have spatially referenced data, space is much more challenging than, say, time series analysis, where the recursive arrow goes in one direction. The past influences the future doesn't influence the past. But in space, there's all kinds of dependencies. You're your neighbor's neighbor, so what you do to your house affects the price of your neighbor's house, and what they do to their house affects the price of your house. So dealing with those multi-dimensional and simultaneous dependencies really is one of the core reasons why spatial analysis is different from other types of statistical analysis. And then the visualization layer that has interfaces to the rich ecosystem in Python for scientific visualization, but trying to specialize it for different types of geo visualizations that we'll talk about. So as Eli mentioned, we're both members of the PySAL team, and we're thrilled to be presenting on behalf of the team. It's a very large team. It's an international team of developers who work on different parts of the library, and hopefully after today's session, you'll get excited and want to join the team. It's a wonderful community. We're both thrilled to be part of it. So that's the context for PySAL. It's a vector, it's primarily focusing on vector spatial data. So we're not going to be dealing with things like rasters and earth sciences here. There's very good packages in the Python ecosystem for that. We're focusing more on the social science side of the ledger for the workshop and for PySAL. In terms of what we're going to be covering today in the plan of attack, so to speak, is in the first half, I'll introduce the fundamentals of the library. We'll look at geoprocessing. So how do you deal with different geospatial formats? That's step one for any spatial analysis. And for those of you who've done any large-scale analyses that involve spatial data, data processing, data harmonization, coordinate reference systems, that tends to be the lion's share of your time and effort. The fun part, the visualization, the statistical modeling, that is a much shorter fraction given the complexity of spatial data. So it's important to have efficient ways to deal with spatial data. We'll look at some ways to visualize our data, geovisualization and different choropleth mapping methods in PySAL. Then we'll talk about this notion of spatial weights, which allow us to formalize the relationships in the spatial dependence in the data. That is the potential for interactions between census tracts or towns or nodes on a transportation network. The global and local spatial autocorrelation tests, these allow us to test whether a map pattern is random or not. Is there something going on in the pattern that we want to further investigate, or is the pattern random? Many things in the social sciences are not random in space. There's good reasons to believe that. Theory tells us that we should expect to see clustering of values in space, and these methods are designed to identify and detect those. Then we'll take the big break. We'll have a shorter break halfway through the morning session, the first part of the session. And then part two, Eli will take over and talk about the application of some of these somewhat abstract concepts to concrete important issues in the social sciences, primarily geodemographic analysis and the analysis of segregation, ethnic and racial and class segregation. Okay, so that's the plan of attack. And then I'm going to jump over to the first notebook. So I'm running in Jupyter Lab, and let me go up to, if you go to the content directory, your screen.
Sorry, there's a request to make the text size bigger.
Bigger? Okay.
We can barely see.
Okay. Let me know when it gets big enough. I'm going to go back to the single screen in a second here.
Okay.
So in the content directory are all the notebooks we're going to cover. I have some exploratory notebooks you won't see, but the key ones are numbered 00 through 06. Those are the notebooks that we're going to be going through today. So those live in the content directory. I'm going to close this and get back to the notebook. So I'm going to start with the geoprocessing notebook, 00 underscore geoprocessing. And in this notebook, we're going to introduce you to the complexities that you confront when you have geospatial data. Geospatial data comes in a rich variety of data models and formats, and therefore you need to be conversant in what these are and what's the right way to read different packages, different formats. What do these different formats allow us to do? And along the way, we're going to look at GeoPandas because it's an excellent package for processing geospatial data. We'll read two different types of geospatial data, GeoPackages and shapefiles. We will confront the issue that is common when you are harnessing data from different sources.
There's a second request to stretch your window if possible.
Sure.
Yeah.
Yep. Make it bigger. How's that?
The window is now bigger, but we maybe zoom in a bit. Yeah.
Make the font smaller?
Make it bigger. There's a suggestion in chat to maybe share desktop instead of one window. That might help.
Okay.
Yeah.
Let me close another window. How's that?
Yes, it's completely stretched. Now you only need to zoom in.
I'm not sure what you mean by zoom in.
Like increase the size of text.
Okay.
Yeah. That makes it, yes.
Is that good? Or too big?
Make it slightly bigger if you can. Yes.
Okay. Everybody's good? Hopefully this will work. It could make some things, we might have to zoom back out when we get to the visualizations.
Okay. Thank you.
Okay. So this is what this notebook does. We're going to deal with having different coordinate reference systems, and those are the way we encode locations on the Earth's surface. There's different ways to do that, and different data sets can sometimes have different coordinate reference systems. So to harness and integrate those different data sets, we need to have them geo-referenced in the same way. We'll talk about spatial joins. That's the ability to create new variables in one data set based on the spatial relationships between observations in two data sets. It's called a spatial join. And then spatial aggregations, which allow us to count, for example, how many of one type of object are inside another type of spatial object. So we'll do a little example where we want to measure accessibility to public health care, behavioral clinics, let's say, and the clinics we have addresses for those clinics, and we want to measure for each census tract how many clinics are in a given census tract. So we have two different data sets, we want to integrate them and do those types of queries. So we're going to start with reading geo packages. The data sets are installed with the workshop, so you'll have these. This first data set is for census tracts in Southern California, 10 counties in Southern California. I'm currently in San Diego. Eli's up in Riverside, just to tell you where we are. And we have a package called Geosnap that's produced as part of the Center for Geospatial Sciences at UC Riverside, and it consumes a lot of PySAL. So it does many different things, some of which you'll see later on when Eli takes over. So we use Geosnap to create a data set called a geo package. And this is an open geospatial format that under the hood uses what is known as an SQL-like database that it can store a variety of things. It can mix vector and raster data sets in the same bundle. You can combine attributes, the non-spatial data, so to speak, and then some extensions from SQLite. So it's a fairly recent format, but it's going to become more common as we go along because it's very flexible. We're going to use GeoPandas to read it. So I first import GeoPandas and I alias it as GPD. The data that we're going to read lives in the data directory, and it's called scag_region. SCAG is Southern California Association of Governments, .gpkg. So that's the suffix for the geo package. When we read that, it's creating an object that is a geodata frame. So GeoPandas, you can think about it as pandas for geospatial data. That's hence the name. And pandas have this powerful class called a data frame, and GeoPandas creates an extension called a geodata frame that has columns that have the data, the attributes, so we can get a list of them. There's a lot of them in this data set. This is census data for census tracts in Southern California. Things like the population of Asian under 15, Hispanic over 60, so the age distribution and ethnic and racial distributions, as well as information about housing units and so on. And we're going to be using this data throughout today. So the columns, if you want to understand the structure, Pandas is basically like an Excel spreadsheet, if you will, where the rows are going to be our census tracts and the columns are the attributes. And these attributes or columns, they hold the values for our particular variable. And the values in a given column are for each one of the census tracts. In our data set, it's a geo package, and you can have multiple layers in a geo package. If you did have a data set with multiple layers, you can use a package called Fiona to get a list of the layers in the package. And in our case, we only have one layer tract. But if you had a data set, a geo package that had multiple layers, you have to tell it which layer, you have to tell GeoPandas which layer do you want to read. Here's an example to do that in the event that layers had multiple elements, not just the one tracts. So that's how you would specify which specific tract, which specific layer to read in. Because we only have one layer in our geo package, when we read it in, we did not have to specify which layer to read in because there was only one. All right. So we read our layers. Do it again here. It will give you the same thing. It's going to be geodata frame. Since geodata frames are essentially data frames, we have all the power of a data frame. So one common method that we call on a data frame is head. That gives us the first 5 rows of the data frame and some of the columns. So we see right away the population age under 15 in this first census tract is 58 people. Okay, the Hispanic population under 15 is 223, and so on. Then we move on to census tract, second census tract, and these are our first 5 records. Right, there are 194 columns or attributes in the data set, and we'll see how many tracks in a second. The shape attribute of the data frame returns a tuple with 2 values. This is the number of rows in the data frame, and this is the number of census tracts. So in the Southern California region, we have 10 counties and 4,580 census tracts, and these census tracts are polygons. And then for each one of those 4,500 census tracts, we are measuring 194 attributes, typically demographic information for each tract. So it's a fairly nice size data set for the kind of work that social scientists interested in spatial analysis would encounter. The columns, the attributes, what distinguishes GeoPandas from GeoPandas geodata frames from a regular data frame is that there's at least one column that holds the geometry. And we have a column called geometry. By convention, it's called geometry. And that column is populated with values that are special. They're spatial. So they hold the geometries for the spatial units. For example, if I ask for the geometry, that's like asking, give me the values for one of the columns. In this case, it's the particular column called geometry. And that lists out this thing called polygon. So the first census tract is a polygon for its geometry. And the polygon is a spatial data structure that encodes a set of XY, or YX, I should say, XY, XY, XY coordinates. So these are the latitude and longitude, or longitude and latitude rather, that trace out the coordinates for a polygon for that first census tract. Then we go to the second census tract. It is also a polygon, and it has these locational coordinates that would allow us to draw the polygon when we visualize it, and also to do different types of spatial queries and analysis on that column. How far away are there different census tracts from one another? Are they contiguous? Those become very important later on when we get to spatial analysis. All right, so we have a bunch of polygons for our column. We can then call the plot method on our geodata frame. And I don't know how this is going to look. Oh, that's not so bad. And my screen is very large at the moment. So this will draw those polygons. Under the hood, what is going on is we're reading that column, the geometry column, and getting the vertices for each polygon. And then between GeoPandas under the hood and Matplotlib, we're rendering the polygons in Matplotlib. So as you see in Los Angeles, the polygons are very small. The census tracts are much smaller. As you get to the eastern part, in the eastern northern counties, the density, the population density is much lower. So the census tracts become bigger and they cover more area. The census tracts themselves, just a little background. The US Census uses census tracts to encode roughly 4,000 people in a given census year. And so clearly, when you have a lot of population density, the census tracts are going to be smaller than when you have low population density, where the census tracts get bigger. So that's what they shoot for, roughly speaking. We had one column in the data set, GeoID, and that has the FIPS codes for each census tract. And the FIPS codes are the federal government's system for distinguishing different spatial units from one another. And they are hierarchical, so they go from state to county to tract and so on. And we'll be using them later on in some of the exercises. Since I can't see the questions right now, I'll ask, are there any questions, and how's the pace? And then maybe Eli can tell me. All right, I'll keep going along. So we have one data set that are the census tracts for all the counties in Southern California. We're going to look at a second data set that comes in the format of a shapefile, and shapefiles are a legacy data set, data structure that comes from Esri, but they've been around for a long time and they're very commonly encountered, but they're probably going to be replaced by the geo packages moving forward. And this data set has addresses for mental health provider locations in Riverside County. And Riverside County is one of our 10 counties. So we're going to read the point shapefile. Again, is in the data directory. And it's a smaller data set, so it doesn't have quite as many columns as the tract data set. So we have the site name, the address, the city, and the zip code, as well as the geometry. We created a data frame, clinics_data frame, and we see that when we call the head method on the clinics, we'll get a peek at the attributes. So scrolling over to the right here for geometry, we see that we have a different geometry type. These are points. Number one, they're not polygons, so it's a different type of spatial data. And the coordinates are very different from the other coordinates if we peek at them. And we'll encounter this later on. We can plot this data frame. So we see a bunch of points. These are addresses, and they're treated as points in a vector spatial data frame data set. We have points. These are the addresses, and the coordinates are very different from the coordinates in the tract data set. We look at the geometries, again, points instead of polygons, and the X and Y coordinates. The addresses are another attribute in the data set. So they give us the street addresses for the clinics. And note that if we ask how many of them are unique, there are some addresses where a provider is able to list different types of services. So they're encoded multiple times by the data source. So we have these two data sets. We have the clinics, which are the behavioral, where people go for mental health services. And we have all the tracts. And let's say we're a public health epidemiologist who's interested in equity issues. Are certain populations in Riverside suffering from less access to mental health services? So we want to narrow down our focus to Riverside County, because that's where we have the data on the locations of the providers. In order to do that, we're going to have to first extract just Riverside County, the tracts in Riverside County, out from the larger data frame so that we can zoom in a sense, on Riverside County. There's many ways to do this, and we're going to leverage some of the functionality that's basically just pure pandas. This is not anything geospatial. Here, we know that the GeoID variable in a data set has that 11-digit FIPS code for the census tracts. And if we read the background documentation that was linked to, those 11 digits, the first two are the state code, so 06 is for California, and then the next 3 digits are for the county code. They go from 001, 003, all the way up to whatever, there's 58 counties in California. So we know that Riverside is county 00065 in state 06. And what we're doing here is asking to do a Boolean, say select out the rows of my data frame where the GeoID for a census tract begins with 06065. And that will create a new data frame I'm going to call RC for Riverside County. And when I plot that, we no longer have all 10 counties, or only have Riverside County. So this is a way to extract a subset from the data set. Okay, so we now have a smaller census tract data set, just the census tracts in Riverside, and let's see how big it is. There's 453 census tracts in Riverside County. Okay, much of the population is in the western part of the county. Again, the census tracts are much smaller where you have higher population density. And then this is the desert, basically. For those of you who know, Joshua Tree is out here. And then to the right, you hit Arizona. Okay, so it's about 112 mile wide county. All right, all the attributes come along for the ride when we do this extraction. So we still have the 195 columns for the demographic data for each census tract in Riverside. All right, so we've created a new data frame for Riverside County. Now putting our epidemiologist hat on, we want to know for each of these 453 census tracts, how many of these clinics does each census tract contain? So it's a crude measure of disparities in accessibility to health services. So we're going to create a new variable ultimately for our tract data frame, which is going to tell us how many behavioral clinics are inside that census tract. When we started, we didn't have any information about that variable in the original data frame. So this is a way of using spatial relationships to create new data that then later on would be used in some type of modeling exercise, testing whether there are disparities, for example. Are the tracts that are high minority tracts that are void of public health or mental health services, for example. But here we're building those variables that would inform that type of analysis. Okay, so we want to know how many clinics are in each census tract in Riverside County. To get this, we're going to use what's known as a spatial join. And the idea is, in our points data set, we know where the clinics are, we know where the census tracts are, but we'd like to put the two data sets together and create this new variable for the census tracts that tells us how many clinics are in each polygon, right? And this is done with the sjoin method of a geodata frame. So the syntax is we're going to create a new data frame that I'm going to call clinics_tracts. And it is obtained by calling the sjoin method. Sorry, it's not a method. It's a function in GeoPandas. We're going to pass in the clinics data frame and the Riverside County tract data frame. And the operation is within. So this is going to be a spatial join that tells us which census tracts are within which behavioral points, behavioral clinics are within which census tracts. When we do this the first time, we're going to get a pink warning box from GeoPandas that alerts us to something very important. And that is that these two data sets have different what are known as CRSs, coordinate reference systems. And these are the ways data is georeferenced on the Earth's sphere, on the surface of the Earth. So the left coordinate reference system has this code EPSG2230. The right CRS is a different code, and you can look these up. The upshot here is that we're not going to be able to know which point is within which polygon because the points have a different coordinate system than the polygons do. All right, so let's peek under the hood and see what's going on. The clinic data frame, which is the point data frame, that's its code for its CRS, EPSG, European Petroleum Survey Group, I think it is, 2230. That's North American Datum, 83. The key thing here is that these are in feet. So the measurement, what those coordinates represent are feet from some origin. That's what the X and Y coordinates are in the point data frame. All right. For the tracts data frame, RC, the Riverside County tracts, that data frame has a different code and it's in latitude and longitude. So those values in the geometry column for the polygons are in degrees, latitude, and longitude. So this won't work if we ignore these different coordinate reference systems. So what we want to do is put them in the same coordinate reference system before we do the spatial join. And you can do it either way. What I'm going to do is put the clinic, since this was the result of our join, it didn't work. If I go back up, when we did the join, we got the warning, and the resulting data frame that I was trying to create is actually empty. So I'm down here now. There's 0 rows, meaning the spatial join didn't find any cases where a clinic was inside a census tract because the coordinates were different in the two systems. So we're going to fix that and redo the join. We see that the tracts are in latitude and longitude, right? Longitude is the x-axis, latitude is the y-axis, and those are in decimal degrees. And we're going to change the coordinate system for Riverside counties using the 2CRS method on the data frame. So I'm saying change the coordinates of the tract data set to those of what I'm passing in here is the CRS of the clinics data set, and then plot this. So when I plot this, you see that the values on the X and Y axis change. They're no longer negative for longitude in the Western hemisphere and positive for the Northern hemisphere, decimal degrees, but rather they're back to the coordinate units of the clinic data set. So these are in feet, right? I did not save this because typically if you want to try something to get it right, I never assign that until I get it right. So now this works, and what I'm going to do is repeat it, but assign it to rewrite the Riverside County tracts. So now that they have the same reference coordinate system as the clinics, and we repeat our join, and we see that voila, the clinics tracts now works, the join worked, and we know for each object ID, these are the points. Index right tells us which census tract in terms of 0 through n-1 number of tracts. Which census tract does that clinic is that clinic contained within? Right? Which census tract is that location, that point falling within? That's what the spatial join does for us. All right. So we have that for all the 28 clinics. So we're getting close to what we need. What we want to do is determine for each tract how many clinics fell in that particular tract. All right. What we've just done is figure out for each clinic which tract is it in. But now we want to sort of flip things around and find out for each tract how many clinics are contained in that polygon. And here we can leverage some wonderful blending of GeoPandas and pandas. Here we're going to do a group by on the clinics tract. And what we're going to do is check in the clinics tract data frame that we just created. We want to count how many times the GeoID appears, because that'll tell us how many times a given census tract, its GeoID, was returned in the join, i.e. how many times does one tract have a particular clinic. All right, so when we do that, we're getting back the GeoIDs of the census tracts, and that tells us how many clinics fell in a particular census tract. And again, I'm not assigning this yet because it takes trial and error to figure out to get it right. Once I get it right, then I'm going to save that to yet another data frame that's 16 by 1. So these are the 16 census tracts that have at least one clinic inside them. All right. Okay, a quick point about this workflow. What we're typically doing is we do a spatial join, we create a new data frame. We extract Riverside County tracts into a new data frame. We do this join, we do this group by, we create a new data frame. And that might seem very inefficient, but for those of you who work with desktop GIS systems like ArcGIS or QGIS, you know that a workflow is typically involving creating new shapefiles or new geo packages for each type of query that you do or each type of spatial analysis that you do, but you're typically doing it by pointing and clicking on a GUI system. The advantage of doing this with notebooks and in Python and scripting is that you will not forget what the sequence was. Your script is basically allowing you to reproduce all those steps, whereas in a GIS system, it's really easy to forget what did I do after step 2 and 7, right? Because it's clicking and pointing, right? So that's a really powerful reason to move to this type of way to do GIS. All right, so we're almost done with this. We know that there's 16 tracts that have at least one, and that implies that there's a lot of census tracts that do not have a behavioral clinic inside their boundaries. So we'd like to build a new variable in the Riverside County data set that has that information, right? And we can do this with leveraging pandas. Basically, we're going to merge, do a table join, our Riverside County tracts data set with this new smaller data frame we just created that has 16 rows. And we're going to join on the GeoID column because they both data frames, the Riverside County tracts and this census tract or the clinic tract data set have the GeoID. So we're going to merge them together by matching rows of one data set that have the same value for GeoID as one or more rows in the Riverside County tract data set. So that's called a merge. And this gets us part of the way, but not completely where we want to go. It only matches the 16 tracts that have at least one, and that's not what we want. What we want is to certainly pull in those 16 tracts that have at least one tract, but we'd also like to know which of the tracts do not have any clinics, because those are the ones where there's potentially disparities. So we're going to change the way we do the merge and use an outer join for those of you who know database table join methodology. Okay, so this gives us a much bigger result. It gives us, now it returns all 453 tracts. And again, I did not save that. If we scroll to the right, we'll see that for the tracts that did not have any census, any behavioral clinics, we get an NAN, not a value because there was no match. And that's okay because we want to know those tracts do not have any clinics. And we can fix that by filling those NAN records with a 0. And that's from GeoPandas. So those become zeros instead of NANs. Scroll all the way over. That's no longer an NAN, it's a 0. And I'm happy, so now I'm going to store this and rewrite my Riverside County tracts. And what we've done is we've created a new variable in that data frame that has for each tract the number of clinics inside the tract. And that is 28, which is true. There's 28 tracts in the behavioral clinic data set. And I'm going to rename that column, instead of it having index right from the join we did earlier, I'm going to rename it to clinics so that it has a mnemonic meaning to me, and see that it's fine. So our Riverside Clinics now is a GeoPandas data frame. And if I ask for RC clinics, we'll see that we have the count of the number of clinics in each census tract. That was the goal of this exercise. Okay. All right, so we have time for an exercise here. What we want you to do, well, let me stop here and ask if there's questions. I'm going to stop sharing for a second and go back to any questions? All right, I'll go back. Share screen again. Okay, so we're going in good pace. Fantastic. So go back to the notebook here. So we have an exercise, and we have exercises peppered throughout the different notebooks. And the way these work is there is a solution to each exercise that if you want to peek ahead, you can look at the solutions, but we would encourage you to try and do it on your own first. You should get it fairly quickly. Some of these are more involved than others, but you have the solutions if you want them. You delete the pound sign and run that cell, it'll load the solution. But those are for later. We're going to give you some time to work on this, and we'll open up for questions so we can do this together if you want to. So the exercise for this first one is you have this shape file that has 10 counties, and you might want to subdivide that shapefile and create shapefiles for each county individually. All right, so what we want you to do in this exercise is do that. We want you to create a shapefile for each of the counties from the larger data frame, and for each county, write that shapefile into a file with the fits code.shape. So the name would be whatever the county is. And for Riverside, it was 06065.shape. Okay, and the FIPS codes are available from up above, and they're also extractable from the data frame. All right, so that's, we have about 5 minutes before about 10 minutes before the first break. So let's say we take 10 minutes to work through this. I'm gonna stop sharing screen because then I can see if there's questions. So ask questions if you're stuck, or share some of your ideas as to how to solve this first exercise. Hello.
I'm back. I think sometimes it's useful for me to be able to toggle my sound back on so that I can either respond quickly to the chat or let Serge know what's happening in the chat if you can't see it. So just leave me on and I'll keep myself muted most of the time.
Okay.
Okay, sounds good.
Thank you. Okay, does anyone have a solution they want to post into the chat? All right, we'll go through the solution we had, and if there's comments, questions, we can cover those. So let me share screen again. All right, so we're back. Everybody can see the notebook, I hope?
Yes.
All right, so what I do here is I'm just going to copy that cell so you have it later. To execute these solution cells, what you do is delete the pound sign or the octothorpe, execute the cell, and that'll go grab the code in the file 00pi and put it in the cell. And then if you run it, it'll provide a solution. So a solution. What we're doing here, it takes a while because it's writing out to the disk. We get that GeoID variable and pull out, as many you pointed out in the chat, get the first 5 units for the fits code to get the tract. And then what we want to do is we're creating that and storing as a new column in the data frame. Here we ask what are the unique values for that, and then write that out. And I actually think there's a mistake here because, well, there's the extra credit question. Okay, so what this should be doing, and this is why it's taking a long time, is writing out to, it's basically going to be writing out 58 county files, or whatever the number is. Okay, so GeoPandas, the data frame inside the for loop, has a method called to_file that will write out to a file. Here I'm using Python fstring to create a shapefile, and shapefiles by definition convention have a .shp extension. The fstring allows us to substitute the current value of county in the loop. So it's looping over the unique county FIPS codes and writing them out to the directory called data with the name 06065.shape, 06073.shape, and so on. All right. All right, so that's where the solutions are. I'm going to stop sharing. And it's time for a break. We're right on spot on time. So we're going to take a 5-minute break now. And we'll come back and, well, you guys can take a break. I'm not going to go anywhere, but go get coffee. Let's say we're going to start back up at, say, 1 after the hour. You guys are 2 hours ahead of us. So I think it's 10 o'clock there. So Ian's saying there are lots of files. Yeah, each shapefile it's a little bit of a misnomer because a shapefile is actually a collection of files. You have the .shp, .shx, .cpg, and some others sometimes. They provide different information about the same data set.
Just as
It wasn't a mistake. It worked.
We're demonstrating file formats that are officially supported by the Open Geospatial Consortium, OGC. So these are shape files and geo packages and GeoJSON and that kind of thing. But just so that folks are aware, there is a brand new capability in GeoPandas that allows you to write parquet files and feather files. So if you've encountered those elsewhere in other tutorials or in other data sets, they're wickedly fast columnar storage to read and write. So in GeoPandas, you can now write out a geodata frame as a parquet file, and it's super storage efficient and really, really fast. We didn't demo it here because it's brand new and it's not officially a geospatial format, but it's good to know about because it's so performant.
So Michael's comment before about step 1, add a county attribute, step 2, question mark, step 3, profit, exclamation point, reminds me of a really hilarious thing I saw at SciPy a long time ago during one of the tutorials. I was sitting in the back of the room and people were trying to get it set up for this one particular tutorial, and someone remarked that the instructions for getting set up for this tutorial were step 1, install these dependencies, step 2, tell us how you did that. And it's gotten a lot better than it used to be. It used to be really a lot more challenging to get your software set up. But because of things like Conda and all the excellent work in the packaging world, it's so much better now than it used to be. Yeah, Eli, there's a really good question. Maybe you should take this one about sources for shapefiles and certain geographies, zip codes, CDs.
Yeah, so I just sent you the link to a package that is part of the PySAL ecosystem called SciPy, and that's a really nice way to grab data directly from the census. If you want to download data manually, I just sent in the link for the Tiger line files. And one final resource I'll give you is that Serge mentioned in the beginning that we're also developing a package called Geosnap, and I'll put the link into the chat here. And Geosnap is designed for working with neighborhood level data, so it comes basically packed, as I mentioned, using these Parquet files, so it's really efficient and fast. So it comes packed with 30 years of census data. So if you want to analyze tracts anywhere in the US, that's a really good way of getting started really fast. Of course, if you want shapefiles for Canada or for the Sudan or somewhere not in the States, you're gonna have to find a different source for that. But now there are getting to be lots and lots of good packages that will go and grab data directly from the API. So I think Census is another one that does the same thing as SciPy. I don't think that's an R package, but maybe I'm getting that mixed up.
Okay, I think we're back from break. We're going to roll on to the next notebook. So we're doing those in order. We did 0, 0. We're going to do 0, 1 now. So let me share screen. We will stop in another hour and take the longer break, a 20-minute break, and then Eli will take over in the second half. Okay, so back to Jupyter. So moving on to geovisualization, 01. Is the size okay? All right, so now we're going to talk about visualizing our geospatial data. When we started PySAL back in the dark ages, our intention was to focus on computational aspects of spatial analysis and developing new methods for spatial econometrics, spatial cluster detection, spatial dynamics. And we didn't want to do any visualization because there were GIS packages back in the day that what you would do is generate the output of your analysis and then import it into ArcView, I'm dating myself, and visualize it there. So we didn't want to spend our time writing geovisualization because that's not where our expertise was. Rather, we were going to hand that off to other parts in the stack. But over time, people want to do exploratory spatial analysis, quick and dirty visualizations inside of PySAL and not have to then go to a second package, fire up a desktop GIS, create a new import the shapefile you just generated and use point and click to generate your views. So what we've done is we started adding the capability to do some visualization inside PySAL, but also we partnered with these desktop GISs so that they can use PySAL inside the QGIS or ArcGIS, and you don't have to use Python separately from these packages. And there's also other packages in the geospatial stack, namely GeoPandas and GeoPlot and GeoViews, that we can interact with for very efficient exploratory workflows. So we're going to demonstrate some of those here. Right, so we're going to use a module inside the PySAL ecosystem called Map Classify, and its job is for choropleth maps, where you're going to use color or a hue to depict the spatial distribution of some attribute across polygons. You want polygons that have a high value for that attribute to be distinguished by a dark color, for example, whereas polygons that had a low value, you use a lighter color, different intensity or saturation or hue. So map classify's job is to tell you, how do you determine how many classes on your map, and given the number of classes you want, how do you determine what the breaks are in the attribute value distribution? We're going to use our same data, so the SCAG data. We're going to change the coordinate reference system so that it looks okay on our plots and has meaning. And here's our first realistic map. So I'm going to show you the map, and then I'll jump back up to the code in a second. This is housing values in the census tracts in Southern California using the defaults, which are a quintile distribution. So we're using 5 classes, and map classify returns these breaks. So we have open and closed intervals for the bounds. So this is a closed interval. The lowest value in the data set is $10,000 for a median housing value tract. The highest value is over $1 million. Okay, so the upper bound in the data set is the max, that's the min, and those are both contained in those intervals. The first interval, the first quintile of housing values goes up to $272,000. That is also contained in the first interval. But the second interval, the second quintile, does not contain that first value, right? So it's open on that lower bound. That's the symbology. That's what that means. So that's the classification. And then we're using the default colors to plot that. So here's the way the diagrams are generated, the maps. We're using matplotlib to get an axis. We're using subplots with the figure size 12,8. So this is matplotlib. The geospatial plotting part is telling the data frame. We're calling the plot method on the data frame. So our geo-data frame is all those census tracts in Southern California. We want to plot the particular column called median home value. The scheme is the map classify classification scheme. And here we're using quantiles, and the default is 5 classes, so they're quintiles. We're going to plot it on this axis object that we created up above. The edge color is the color for the polygon boundaries, those lines. And when it's white, we turn the legend on true, and we're using a line width of 0.3 for the width of the legends. Okay, and then we turn off the X and Y axis so you don't see the coordinates, and we plot. All right, so that's using GeoPandas to do the plotting. The plot is a method that belongs to the data frame, really powerful functionality. And under the hood, it's using map classify for the classifiers. So that's a really nice interaction between the two libraries. All right, so this is a first cut. There's obviously issues. You have really small tracts where there's high population density, but the idea of these visualizations is to give you a view of the spatial distribution of that attribute value. And we're going to start asking questions. Someone asked, what does spatially random mean in the question before? Does that map pattern look random to you? Meaning, are the high value census tracts distributed randomly on the map, or is there clustering? That is value similarity in space. Visually, this is challenging because these polygons are not all the same size. Your eyes are drawn to the big ones. They're also not all the same shape. So it becomes really tricky to not fool ourselves about that question, relying solely on visualization. And we'll see later on in the second part of today's tutorial, we have quantitative statistical measures that we're going to use in conjunction with these powerful visualization methods so that we don't fool ourselves. Maps are really powerful. They get a lot of press. You look at the New York Times, pretty much every other day, there's a map of COVID outbreaks. And people are drawn to maps, right? But they can fool us, and we'll talk about how not to fool ourselves later. All right, the other problem with this is unless you're a Southern Californian, you may not know where this stuff is. And even if you are a Southern Californian, you may not know where Riverside County is, or the city of Riverside, or the city of Long Beach. So we want to add some context, and we're going to use the package contextually to do that. First, we're going to do a little cleaning up of the data set. and use the same plot method, but we're adding another layer, which is a base map. And this will take some time because it's going to pull in tiles from a server somewhere. There we go. And you'll start to see the layer from contextually that has an image that has the names that'll provide for context. So now we know where Palm Springs is. We know where San Diego is. We know where Riverside is. So we now have a lot of information visually to process. We have the choropleth map, with the lighter colors being the tracts that have very high housing values, median house values. The darker hues are the lower housing value tracts. Okay. So let's look at these classifiers a little bit under the hood. I'm going to pull out the median housing value attribute from the data frame and stick it in its own object. So that is our series. Those are the housing value, the median housing values for each of the tracts. And now I'm going to explore what MapClassify can let us do. We call the quantiles method from MapClassify, pass in the particular attribute that we want to classify and specify the number of classes we want. So we say we want 5 classes, so that's going to return 5 classes. And it's a quantile classifier. So how does this work? We sort the 4,580 tract values from low to high. And since it's quintiles, we're going to split it into 20%. So the first quintile, the 20th percentile, the data set is a housing value of $276,000. Okay. The maximum we've already seen is $1 million for the median value, right? The 80th percentile, 628,000, and so on. Then the counts should be roughly equal because it's quantile, so it's the equal number of polygons in each class. But because you can have duplicate values and ties, it sometimes doesn't work out that way, but it's close to that. We could change the number of classes. So instead of 5, what if I wanted 10? Same call, different value for the K parameter, and you'll get the deciles now instead of quintiles. All right. If I assign that into an object, Q10, that object has a lot of attributes and methods that you have at your disposal that GeoPandas uses under the hood. One of the attributes is the bins. So these are the upper bounds of the deciles, right? That's the 10%, 20 percentile, 30 percentile, so on. The counts is an attribute that tells you how many tracts fall in each of those bins, and so on. MapClassify also has a number of classifiers, different classifiers. So if we look at it has quite a few, depending on the type of data you have. We're only going to look at a couple of them today, but this is for future interested readers, so to speak. The Fisher-Jenks classifier is an optimal classifier. So this says, I want 10 classes. Define the break such that you're minimizing internal heterogeneity, meaning the difference in the housing values for the tracts assigned to a particular class is minimized, but the values across the bins are maximized. That's what Fisher-Jenks is trying to do. And it is an optimal classifier, but it can take some time on large data sets. So it's not going to necessarily give us equal number of counts in each tract, but rather it's trying to split the data into meaningful, statistically meaningful classes according to this objective function. And to see that, we can compare its measure of fit. A lower value is better. So the Fisher-Jenks classifier has a lower fit, less error, if you will, than the quantile classifier with the same number of classes. And that will always be the case. Fisher-Jenks will dominate all the other classifiers for the same number of classes. All right. So the other nice thing about MapClassify as a library is, let's say you did want to use Fisher-Jenks or box plot or standard deviations or quintiles or whatever, but you had your own bins you wanted to use. You can do that. You would specify the bins. Let's say I wanted to use these as the upper bounds for my classification. And then I pass those in. So this would be $1.5 million for the upper bound. Then it will classify your data given your pre-specified bins. And you get an object back that has the same attributes as any other map classify object. All right, so that's a little bit about map classify. GeoPandas uses map classify under the hood. So we've already seen that. Going back to our plots. Right, so these binning, the binning comes from GeoPandas taking the column and calling the relevant method in map classify and then bringing back the classify object to do the rendering of the legend and the coloring of each of the polygons. All right, we're going to play around with some changes here. So we're going to change, I think we're playing around with the classifier. Yeah. So here, this map was for quintiles, 5 classes. Here, we use the same styling, but we changed the classifier to Fisher-Jenks. Remember, that has a better fit. So the spatial patterning is going to change because each track may now be assigned to a different class than was the case when we use quantiles. We can also change the color scheme. So I'm changing CMAP, the color map, to blues. Depending on the type of data you have, there's a rich literature on the choice of color maps. Depending on whether you have sequential data, which we do here, or categorical data, or diverging data. We're not going to go into that too much today at all. And then the same thing, same color scheme, but with Fisher-Jenks. All right, so those are the 5 classes, optimal classes for Fisher-Jenks and the resulting classifications. So by randomness, we're asking, are these dark polygons, which are the high housing value tracts, are they randomly distributed in this space? And qualitatively, it looks like there's this coastal effect, right, which intuitively makes sense to us if you know anything about Southern California. But we're going to go beyond the visual inspection later on. All right, some things that are nice to do is I'm going to extract the individual counties and generate one map for each county. So what we're doing is, like we did in the exercise before, we're going to get the counties, we're getting that county variable, and getting the unique values by passing that into a set. So here are the unique county IDs in the data set. And then we're going to loop over that set. And for each county, we're going to extract and create a new data frame just for that county, the tracts in that county. And we're going to apply Fisher-Jenks with 5 classes to just the tracts in that county. So now the bins, if you will, are going to change potentially across the tracks. So 0673 is San Diego. This is the county I'm currently living in. And this is the 5 classes from Fisher-Jenks. And that's the spatial distribution of housing values, median housing values across the tracts in San Diego. Okay. Then this is San Bernardino County, which is in the north part of our data set. Again, we're reclassifying just those tracts using the same classifier, but allowing the data to tell us where the breaks are. And so San Bernardino, it's a huge county. In fact, you can fit the whole state of Maryland inside San Bernardino County. So this is a massive piece of real estate. The population is located in the southwest corner of the county. But these are the spatial distribution of housing values in San Bernardino. 59 is Orange County, if my memory serves. Right, so you see a lot of these are particular to San Bernardino, I'm sorry, to Orange County. So if you start to compare these different patterns, this is Riverside County. All right, that's Los Angeles with the Channel Islands. This is Ventura. And then this is Imperial County. All right, so that's a way to generate individual county level maps. All right. Next package we're going to look at is called GeoViews, and this allows for some really nice interactivity. We're importing a lot. We're going to start with a built-in data set in GeoPandas, natural earth cities. So the HV plot, which we're looking at here on the right, these are cities, has some nice features. So the hover tool is on, and as we hover over the points, you have an attribute that's surfaced, so the latitude and longitude. Over here, we have panning that's on, so I can move the map around. We have zooming. If I click that to turn it on, you'll see the blue icon label tell us that's on. Then we can zoom in with a lasso. Put the wheel on. We can use our mouse wheel if you have one to zoom in and out, and then refresh to go back. Right. So that's very nice interactivity from the HV. So let's use this with our data. Our geodata frame, we're going to do an HV plot. The default is not going to look so well because we haven't specified that it's georeference basically. And there's a lot of tracks, so it takes a bit to render. So the star means it's doing its work. So we see that it gets stretched out because it's treating longitude and latitude as XY coordinates when in fact they're spherical coordinates. So we're going to fix that with the way that projection gets done into two-dimensional space so it looks a little bit more familiar. Again, it's going to take a bit because we have 4,000 polygons here. And your mileage will vary depending on what you're running on. This is running on a Nook, so it's a pretty lightweight desktop machine, not very powerful. And here we go. So we get the proper stretching or aspect of the attributes, right? So we haven't plotted any variables yet, any attributes. Those are the polygons. And you can see the density. If we zoom in around Los Angeles, you can see what we mean by those tracks, right? So there's a lot of tracks here. And we have observations for each one of those tracks in the data set. Choropleth with GeoViews is not straightforward. So what we've done is build a little function here. I'm not going to go into the details, but it's going to allow us to generate a choropleth with the power of the GeoView. And plot. And once this is done, we're going to have another exercise.
While we wait, what that function is doing is creating a new column on the geodata frame that uses the labels from map classify, and then we use that new column to tell HoloViews what plot we want, what color we want for each polygon. So Eli's explaining what the function is doing here. So now we have our map, and we can start to exploit things. So zoom into, say, San Diego, and
is very nice, because one of the challenges with choropleth maps is you have this quantization of the data. So you're either in class 1, 2, 3, or 4, and everybody in the same class gets the same color, but there can be variation within that class, right? So we can compare this census tract where it's 680,000 for a median value versus this one where it's a little bit under it. So you see some variance in the attribute values for the same color. So here it's 426,000 versus squinting 380. Okay, so that's powerful, adding to the visualization. Okay, I'm going to skip over these because we're simply changing the color scheme here, and then with Fisher-Jankshin we get a different rendering. And what I'm going to also do is skip over this particular exercise. You can do it on your own later, because I want to get through one more notebook before we break in about a half hour. All right, so that's a little bit about geovisualization, and only a small fraction. There's a lot of different types of geovisualization you can do. This is all about choropleths. There's certainly things like cartograms, heat maps. There's a really rich literature on geovisualization. We're focusing in this notebook just on choropleths, but you can go pretty far with the tool sets that are in the SciPy environment in terms of interactivity. All right, so going back to our list. Next notebook is spatial weights, so O2. So now we're going to start building in some of the infrastructure to test whether these map patterns are random or not, statistically speaking. And then in the second part of today's tutorial, you'll see how Eli's using some of these constructs that we're going to talk about now to do spatial analysis. So the workhorse for a lot of spatial analytical tools is the notion of a spatial weight. And what the spatial weight is a weight that for each pair of observations in our data set, each pair is some, in our case, the census tract I and census tract J. W sub ij tells us about the potential geographical relationship between I and J. Now, what that relationship is can take on different definitions, right? We can ask whether the census tracts touch, whether they are within a certain distance band of one another, and so on and so on. This Wij weight, you can think about it as belonging to a big matrix. If you have n polygons, that matrix would have n rows and n columns. And each value in that matrix tells us about the potential spatial relationship between the observation on the row and the observation on a column, right? And these weights are used in all kinds of spatial analytics that we'll see later today. So LibPySAL, which is part of the PySAL library, that has a module that deals with spatial weights, their construction, their manipulation, their porting to different platforms. So we interact with Stata for the economists in the room and the sociologists, MATLAB, R. There's a lot of different formats that spatial weights get passed around, and PySAL supports all of them. So you can read from R, pull in a gal matrix and do spatial analysis inside Python, or generate your spatial weights with Python and export it to Stata, for example. All right, so that comes from the weights module in libpysal. And we're going to use xplot, which allows us to visualize some stuff about the weights that hopefully will make them a little more concrete. So there's different types of spatial weights. We're going to start with contiguity weights. Contiguity weights are the simplest type. So they simply say polygons A and B are going to be considered geographical neighbors if they share an edge or a vertex. Remember, our polygons are nothing more than xy, 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 those coordinates. And to check for queen contiguity, we take the coordinates from two polygons and we see if there's any common vertices. If there are, it means that those two polygons share a vertex, i.e. they touch. So that's what we mean by queen contiguity here. And we can construct the queen weights from a data frame. We're going to read in our tract data frame. And once we have it in memory, we'll change its coordinate reference system to UTM zone 11N. That changes the values of the coordinates. And then with the queen class from the PySAL, we're going to call the from data frame class method and pass in our data frame. And that returns a queen weights object with a warning. And this warning is really important to pay attention to for your data set, that there are 3 disconnected components, and we'll explain what those are in a second. And there is 1 island tract. Okay, so what is an island tract? That is a polygon, a tract that shares 0 vertices with any other tract in the data set. So it's disconnected according to this definition of connectivity, right? So it's a true island, all right? That's what this is. The disconnected components, for those of you who know about graph theory and adjacency matrices, the components, a component is a group of tracts that are connected to one another in a sense, meaning you can travel from one tract to its neighbors and the neighbors of that tract to another neighbor and so on to get to any other tract in the component. All right, so those components are connected, meaning you can get from one tract to the other by traversing the connectivity, right? But you cannot travel between the tracts of one component and the tracts in another component. They're not, because none of them share a connectivity, a connection. All right, so the queen weights, the class is a contiguity queen object, and they have a bunch of traits that we've designed in the class that are useful for working with the weights directly or later on for different spatial statistical methods and clustering. So we can first find out, okay, for the 155th or 156th, the tract with index in the data frame 155, who are its neighbors and what are the values of the weights? So the tract at index 155 has neighbors with index 4528, 547, 2133, 2744, and the weights are all 1 because it's a binary weights matrix. It tells us I and J are neighbors or they're not. All right, so PySAL figures this out by an efficient algorithm that checks for hits. For those of you who know robotics, finding where there's a shared vertex in an efficient manner. And so the weights is essentially has a dictionary called neighbors that'll tell us who's a neighbor of who. We can add in the self, meaning tract 155. So this is the focal unit, and these are its neighbors, if you want to think about those. Right? And then we can start to look at what's going on with the data set around that focal unit. Right? So there are no Asian Americans under 15 in this tract that neighbors tract 155, for example. All right, the weights object also has the ability, if you want to get the full weights matrix. The weights object itself is very efficient because it's sparse. There's a lot of zeros in the actual matrix. We don't store those. We only store the neighbor pairs. The non-neighbor pairs are implicit. But sometimes you want the full matrix, and you can get it by calling the full object on the W. So our queen object we call full, and that returns a matrix and the IDs. So the W matrix is big. It's going to have 4,580 rows and columns and a lot of zeros because a lot of the tracts are not neighbors. They don't touch. The tracts in San Diego don't touch any of the tracts in Ventura or LA. Other things we can get from that matrix, we can ask how many neighbors does each census tract have? That would be obtained from taking the row sum of every row in the matrix, if we had it. So that's NumPy or NumPy, where sum A across axis 1, which is across the rows. And that tells us, we know that census tract at position 155 has 4 neighbors. But the weights object itself figures that out when we construct the weights, when we create the weights object. So it records the number of neighbors for each unit. We don't have to do the matrix algebra to get it. All right. Another thing we can do is transform the weights. Right now they are binary, but for some spatial operations, you need to row standardize them so that the values sum up to 1 rather than the number of neighbors. And we'll see examples of that later after the break, why. And so we can do that with the transform property. And when we do that, now when we sum across the rows of the transform matrix, they're row normalized. All right, spatial weights are really sparse, particularly contiguity weights. And what do we mean by sparse? The percentage of non-zero values, if you have the full matrix, is 14%. So there are 86% of the values would be 0 in that big matrix. All right, skipping over a little bit of stuff here to get to the plotting. So we're going to plot what the weights look like, and hopefully this will make it more intuitive. These are fairly abstract concepts. So we're plotting. This comes from splot. We imported this function called plot spatial weights. You pass in the weights object and the data frame you want to plot it on, and you see the graph, the connectivity graph for the census tracts. And the way this works is we reduce each census tract to its centroid, center of mass, and that point represents the census tract. And then based on what the queen weights object tells us, whether I and j are neighbors, we add an edge between the nodes of polygons that share at least one vertex, right? And so the density of the tracts here makes it hard to see the connectivity structure where the tracts are solved. But if you peek out to the east, you can see what's going on with the connectivity structure. So this is the type of information that's encoded in the spatial weights object. And later we'll see why that's important when we get to testing for spatial clustering. You need to find who's nearby who, and the weights formalize that notion. So let's do some introspection of the weights itself. There's an attribute called cardinalities, which tells us the frequency of the number of neighbors for this graph. All right, so the mode, I can't remember what the mode is, but there are some tracts that have, a lot of tracts that have between, say, 7 and 8 number of neighbors. Right? There's some tracts that have a large number of neighbors. We're out here, very few of them. And there's some tracts that are very sparse and have 0 neighbors. We saw that there was one island, so there's at least one tract in the data set where there's no neighbors. The cardinalities are tucked away. So these are the number of neighbors for every census tract in our data set. That's in cardinalities.values. So that's queen contiguity. There's other types of contiguity. Rook contiguity comes from thinking about a chessboard. For 2 polygons to be rook neighbors, they have to share an edge. Sharing just a vertex is not sufficient. So rook is more stringent notion of connectivity. And rather than queen from data frame, we call rook from data frame. Okay, we get the same warning. And in this case, for each census tract, we can find out how many neighbors, who the neighbors are, introspect the data around a particular focal unit. So the structure of the weights in terms of the number of attributes is the same across all these classes. The values are going to change depending on the criterion. So if we plot the rook graph, it's going to be sparser because it's a more stringent notion of connectivity. So there's fewer edges on the connectivity graph than for the rook. And the histogram for the cardinalities is also going to be slightly different. It'll shift. All right, bishop weights. PySAL's weights class operates or it surfaces set theory operations on the weights. So you can do things like symmetric difference for adjacency structures, unions, intersections, and so on. And so the bishop weights, if you think about a chessboard, those are the diagonal moves. So we want to know in some problems whether two polygons are bishop neighbors. It's pretty rare in the social sciences to use this, but it's more used in, say, ecology, where you're looking at resource distributions for plants that are competing, or river flows or things like that. But the functionality is in there. If we want to get the bishop weights for our graphs from the queen and the rook, that's simply the difference between the queen neighbors for a polygon and the rook neighbors, because a queen can move orthogonally, but also diagonally, whereas a rook can only move orthogonally. So the difference is the bishop. So with PySAL, we can call weights.w difference and pass into weight structure, and we'll get back a new weight that is the bishop. And we get the histogram for the joins. We see that there's a lot of polygons, 1,600, that do not have any bishop neighbors. There's a lot that have one bishop neighbor, and so on. Okay, and we can plot those just like we plotted the rook and queen. And that's the connectivity graph for polygons that are bishop, so-called bishop neighbors. All right, so those are contiguity weights. There's other types of weights. There's distance-based weights. So we might want to define two polygons as neighbors if they're within a certain distance of one another. All right, so here, this is where your coordinate reference system becomes important, because you have to know if you're measuring feet, meters, or decimal degrees. So we're putting our data into meters here by changing the coordinate reference system. And now with PySAL, we're going to define neighbors as any pair of polygons whose centroids are within 2,000 meters of one another. And that's called a distance band weight. That constructs the weight, and then we'll plot it when it's done. It's using SciPy Spatial under the hood to do the efficient lookup of the distances. And then we'll plot that connectivity structure based on distance bands. Right, so what do we see? That these polygons or centroids are definitely separated by more than 2,000 meters, whereas the joins are where you have the high density tracts. So that's one type of distance weight, although you use distance to define a binary relationship. Another type of distance-based weights are KNN weights. So KNN, here we're going to say we want every polygon to have k neighbors, but those neighbors are its nearest k neighbors. So here we need distance to be measured properly. We have to take the curvature of the Earth's surface into account. So we're going to do it the wrong way. That is, we ignore curvature and then do it the right way, where we say, hey, these distances are on the Earth's sphere, and compare it. So the first way, we're using KNN from data frame on our data frame, where it's latitude and longitude for the coordinate reference system. And we want 8 neighbors. So everybody has exactly 8 neighbors. That's the idea behind KNN. But now we're going to do it the right way, meaning, hey, calculate the distances on the surface of the Earth, not on flat, unprojected coordinates. So this is the right way to do it. Everybody will have 8 neighbors, but the key thing is the neighbors are going to be wrong, or can be wrong, if we ignore curvature and our extent is large enough. So if we look at one particular census tract in position 1487, we'll see some errors here. So 2881 is indeed a neighbor of 1487, but if we ignored the distance, it's omitted. And I think there's one where error of commission where you're including somebody who shouldn't be included. So curvature, even for Southern California, takes into account, you need to take it into account when you're defining these connectivity based on distances. Right, so that falls. All right. Going to skip this exercise, so it matters whether you take curvature into account or not. Going to skip the exercise in this case and talk about the last type of weights. Up to now, all of our weights, whether they're based on contiguity or some distance cutoff, KNN or distance span, the weight itself was a 1 or a 0. I and J are neighbors according to this definition. Sometimes you want the weights to be continuous, not binary. That is, you want to have a weight that reflects a distance to K, meaning further away neighbors should weigh less than closer neighbors or be less important than closer neighbors. And there's many ways to do that. We do it with kernel weights in PySAL. So the idea behind a kernel is you drop a kernel function on top of the centroid and it'll distance decay away from that centroid out to some bandwidth where you cut off. And the weight itself is where you are in the kernel at that distance away from the focal unit. Right, there's a lot to this, just wetting the whistle here and putting it on people's radar screens. We do kernel weights from our data frame. So kernel from data frame, K is 10. We want to use adaptive bandwidth so that you allow for the density of the points to drive what the bandwidth should be. And we use a Gaussian kernel and plot that so you see what we're looking at. All right, so that says who is a neighbor of who with this bandwidth cutoff. But these, if you have the weights, these edges would be not all 1, 0. They would be weighted edges, and the weight would be a function of the value of the kernel at that distance separating the 2 points. The bandwidths are adaptive, so they vary depending on where you are. If you're out here in the east, you need a bigger bandwidth to get at least 10 neighbors. But if you're in the western part where there's a lot of density, you want a smaller bandwidth. That's what the idea here is. And then we can actually plot the bandwidths to make that a little clearer. So these are the bandwidths that were used in defining the kernel weights, and they get bigger in the lower density areas. All right, last group of weights we're going to talk about are block weights. And these are used when you have in hierarchical models, multi-level models, where people are nesting, say, counties inside states, for example, or tracts inside counties, and you want to estimate some type of model that's multi-level. Block weights are a way to define as neighbors 2 polygons that belong to the same regime or same block. To make that hopefully more transparent, we're going to cook up an artificial example. I'm going to get the midpoint of our data coordinates on the map for the X and Y, and we're going to split our map into 4 blocks. I'm going to use Shapely to get the centroid. We'll plot this, and you'll see what's going on. Okay, so the centroid is somewhere around here, and for the whole data frame, what we're doing is saying if the centroid for a census tract is in the northeast quadrant, put that census tract in this block. If it's in the northwest, it belongs to this block, south, west, and southeast. Okay, so we have that attribute in the data frame, which quadrant is the tract in, and then we can use block weights in PySAL, pass in that regime or block variable, and it creates our block weight. And these are dense, so 65% non-zero. And if you plot the cardinalities, you'll see that. So this is the block group that has a lot of census tracts in it, and they're all considered to be neighbors of one another. And we can get the counts. Right, so that's the number of blocks in each group. Excuse me. Sorry about that. This is the number of tracks in each of our blocks. But each block, all these 15 polygons are neighbors of each other. That's the logic for these block weights. Okay, that is it for the weights. I realize we probably went through some dense material pretty quickly. There's a couple exercises that we can go through. A couple exercises we can go through that will help you explore these weights, these concepts interactively. So the questions are, and the solutions are all in one file down here. And you might be able to intuitively answer these without writing code, but you should also write code to verify your intuition is right. Which spatial weight structure would be more dense? Tracts based on root contiguity, or Southern California tracts based on KNN with K equal to 4? That's our first question. Then you'd want to find out how many tracts have fewer number of neighbors when you use Rook versus KNN 4. And then how many tracts have identical neighbors when you use Queen versus Rook? Okay, so I'm going to switch back to stop sharing. We'll do the same thing. We'll give you 5 minutes to work on that. Come back, look at the solutions, and then we'll take a longer break and turn it over to Eli.
Do you want to do the weights disparities notebook?
So, no, because we'll run out of time. We can come back to it.
Yeah, that's what I figured.
Yeah. So the notebook 03 on weights disparities is using the weights to identify of all these census tracts in Southern California, which neighboring tracts have the largest disparity in their housing values. Where do you find the biggest gap between an expensive house and a less expensive house? Well, median housing values. So the measured density is the number of non-zero cells if you have the full matrix over the total number of cells. So it's the complement of sparsity. And the object has a dot PCT underscore non-zero. Just so people know, while I'm presenting, and this will probably be the same for Eli, when I have the full screen, I don't see the chat. So if you ask the question, I wasn't ignoring you, I just didn't see it. But Eli was doing the question and answers, so hopefully things were covered. And I'll do the same in the second half. So I'm looking over the questions. There's a lot. Good job. Awesome. All right. So I'll switch back to screen share and look at the solutions. All right. So KNN 4, everybody has 4 neighbors. That's the definition of KNN versus Rook. So on a regular lattice, meaning a checkerboard, there would be the same, right? But the thing that's fascinating about social sciences is that we never work with maps that are regular lattices. The polygons are always different shapes and different sizes. So your intuition only takes you so far. So let's look at our solution. Reload it. So first we need our 2 weights objects, our KNN 4, that's the from data frame class method. You pass in the data frame, the geodata frame, and how many neighbors you want. We want KN 4, so everybody has four neighbors. And then using f strings, we're going to print the percent non-zero for KNN4. And then similarly for the rook, again, call the class method from data frame, pass data frame, and rook, there's no other arguments. It's defined by how many polygons share an edge, and print out the density measure. Okay, and let's run this. And it's running. So that's the percent density in the KNN4, 0.08 versus the rook, 0.11. So the rook is more dense. Okay. And then for the second and third question, there are 280 tracts that have fewer rook neighbors than KNN neighbors. And there are 1,624 tracts that have same, who is a neighbor is the same whether you use rook or queen. But remember, there's 4,500, so there's a lot where that will differ. All right. All right, so that's the solution for those three sets of exercises. I'm going to stop sharing screen. All right, so it's just about on time. They suggest we take a 20-minute break at this point. So it's 9 o'clock here, which means it's 11 there. Is that right? So let's say at 11:20 we come back, and Eli is going to be going over the second set of materials, and we'll switch positions. Yeah, Vincent, you're right. The weight stuff is very complicated. Hopefully in the second part, you'll see how the weights are used for spatial analysis, and that hopefully will give you more intuition as to why you want them, what they afford. There's a book that I wrote with my co-founder, Luke Anson, on using PySAL for spatial analysis called Modern Spatial Econometrics with PySAL and GeoData. And there's 2 chapters in that book just on weights. So you're right, it is complex. Sometimes we give all-day workshops on PySAL at some conferences. This one's a half a day. So apologies if that was a little too dense for people.
Is the timer still on the screen?
I see it.
Okay, good.
Yeah. Although it paused for some reason.
Okay.
Yeah, there it goes.
All right, I have to stay on that screen then. That's no worries. I was just going to see if I could scroll through the chat. Okay, I will be right back.
I'll stick around for about 10 more minutes, and then I'm going to take a break. So if people have questions, I'm here. If Eli's taking a break. Thank you, Ian. We, at the end, when we close, we'll point you to some other resources that hopefully people will find useful. I'm currently writing a book with 2 of the other core PySAL developers on spatial data science with PySAL, and it's under contract, so we're due to have it done this coming January, but it's online, and you can read parts of it now. Yeah, there's a question. Could you give us some examples of when one would prefer one type of weight over the others? Yes. So the idea, it's a little bit of a catch-22 situation. You typically use these weights when you're, say, estimating a spatial regression model. and you want to take spillovers into account. That is, maybe it's a model for housing prices where your dependent variable is housing prices, and the traditional model and so-called hedonic model is the attributes of the house, number of square foot, number of bedrooms, pool, fireplace, right? But in spatial versions of that, you also want to take into account what's going on in the neighborhood, because the housing values of my neighbors influence my housing values. So to do that, to define who is my neighbor, that's where these weights come in, right? They're going to tell us, all right, the relevant neighbors are the ones where the Wij is non-zero. So there's different philosophies about how inclusive do you want to be versus how short should the model be? Do you want to allow for a lot of neighbors, some of which maybe are meaningless? You're too far away, and therefore there's essentially no correlation between the housing value, say, half a mile down the road versus a housing value within a quarter of a mile, right? Versus saying, well, it's only a quarter of a mile, and therefore those are my neighbors. So it's a little bit of, people do precursors and do try and test what's the spatial extent that we should use. But you get into all kinds of philosophical issues like, well, you're basically building a model that's pre-testing on the data. You need to take that into account. Your inferences are now really convoluted. So that's not a very helpful answer, but it's an honest answer. The queen would be more inclusive because it's less stringent. You only need to share a vertex, whereas the rook, it's to share an edge. And then it has to do with what your philosophy is, and do you want to estimate models that include errors of commission, where including everything, you have a large spatial bandwidth, versus errors of omission, where you have too short of the bandwidth. The rule of thumb, given that there's no recipe, so to speak, that you should follow, always use a queen or always use rook, is to see how sensitive your inferences are to alternative choices of the matrices. So with PySAL, it's fairly straightforward to estimate a model with different versions of the W, for example, and see how fragile are my conclusions to that choice of the weights. In general terms, if they're robust, meaning the story doesn't change, you can feel fairly confident in your predictions and your inferences. However, if things are radically different between, say, using queen and rook, that should raise some red flags that there could be some measurement errors in the data, noise in the data. The coordinates can have errors because of the way the data is geoprocessed. It's easy to create problems in the data with pre-processing. And that might be flagged by very stark differences between models that are estimated with one version of the weights versus another version of the weights. So Zafar, the motivation for the queen and rook come from conceptualizing a regular lattice, right? Where every polygon is the same square, same size and shape. So it's easy to think about, am I sharing that corner vertex or am I sharing an edge? But we use those notions, shared edge and shared vertex, for non-regular lattices. So if you look at our maps of the tracts, they're not all the same shapes for the polygons, but you can still ask whether two polygons share an edge or share a vertex. So what is a vertex corner of a polygon? To draw a checkerboard or a chessboard, for each polygon, for each square, you need 4 points, the corner points. Those are the vertex corners of the polygon. Does that make sense? And those vertices are in the geometry column of the GeoPandas data frame. So is a vertex more than 2 polygons? So is a vertex, I'm not quite sure I got your question, Zafar. I think you're asking, can a vertex be shared by more than 2 polygons? Is that the question? Yes, that is possible. Think about, for the US, the states, the 4 corner states, Arizona, New Mexico, Colorado, and Utah, they share that vertex. So that's, yeah. So a vertex belongs to 1 or more polygons. If you have, say, in our data, the coastal census tracts, some of those vertices are only going to belong to 1 census tract if they're intermediate on the edge of the Pacific Ocean. But there are some vertices for those same census tracts that touch other, that also belong to the northern tract that abuts it.
Sure, Vincent. So I work at the Center for Geospatial. And how they change over time, and to understand how we scale up spatial analytics to really large scale problems. So substantively, my own research, I have a background in sociology before doing my PhD in urban studies. So I'm particularly interested in neighborhood effects and inequality and gentrification and neighborhood change. All right, so we know quite a bit about things like concentrated disadvantage and things like spatial access to resources like good schools or healthy food, and the kinds of impacts that those resources have on socioeconomic inequality and racial inequality in particular. So we spend a lot of time at the center thinking about new ways to try and either model how neighborhoods change or model how neighborhoods affect the people that live inside of them. And sometimes that means developing new methodological techniques. And sometimes it means taking an interesting spin on things that already existed. So when we get to the Geodemographics notebook, geodemographics itself is not new, but something that we're doing at the center is trying to think about a time series of geodemographics and use models that describe how one class changes to another over time. When we talk about the segregation work in the segregation notebook, we have some brand new methods that try and understand whether the difference in a segregation statistic between 2 places is significantly different. So if I measure segregation in Chicago in 1980 and I measure it today, is that difference, has segregation either increased or decreased, and has it done so in a statistically significant way? And we think about ways that you can try and parse out what's causing the difference, whether that's because it was just because there was a influx in Hispanic and Latino immigration, say, and just because you have different population structure, maybe that's what leads to the different statistics that you observe. Or it could be that that the way that the city has developed has changed a lot, but the people there are still the same. So we'll get into some of these issues as we get further into the notebooks. Yes, as in Wallace. No, I mean as in people inhabiting different places, yeah.
I lost the time, but I think it's 20 after.
It is. We should get started. All right. Okay. Can you guys hear me?
Yep.
Okay, good. All right, so while we have just a minute or two, how's the aspect ratio and the zoom? Can people see everything okay?
Maybe make it slightly bigger.
Okay. How's that?
Yep.
Okay. All right. So let's go ahead and get started because we've got a pretty good amount of material to make it through in the next hour or two. So if you have questions, keep raising them, and Sergio will respond to you at this point. But now I can no longer see the chat. So if you have questions specifically for me, save them until the end.
Bump the font a little bit bigger.
Good.
Yeah, I think so.
Okay. All right. So Serge walked us through some of the fundamentals in data structures for performing spatial analyses. We looked at how to subset geodata frames. We looked at how to express different spatial relationships using either selection queries like intersections or using weights matrices that describe how an observation in a study area is related to the other observations in that study area. And so now we'll get to see how you leverage those structures to do exploratory spatial analysis here, and then some further analyses in the later two notebooks. So this notebook really focuses a lot on the ESDA portion, exploratory spatial data analysis, the ESDA module of PySAL. And we're going to look at statistical concepts about relationships between that leverage the weights matrices that Serge just described in the last notebook. So let's just get set up and import what we need. You've seen, I think, all of these before. Let me actually clear all my cells. Okay, so once again, we're going to use this same data set. We're not actually going to use this trees, so let me get rid of that. And we just read in the geo package. And we're only going to work with San Diego. So this time we'll just slice out County 73, like we saw how to do with the Geoprocessing Notebook. Let's learn a little bit about it. And then because we want to analyze home values, let's just make sure that we don't have any missing values in our data. And we're going to convert to Web Mercator so that we've got some nice visualizations. Okay, so let's get a handle of the data that we're looking at. It's always a good idea to generate a plot first. Let's look at median home values in San Diego. Here, we're just using the default plot from GeoPandas, and then we're going to add the base map contextually. So as you may have noticed in the previous notebooks, right, a lot of the high-priced areas cluster near the beach, unsurprisingly, and there's sort of this gradient that goes this way. And so to look at this map, we can start to identify places that look like they are hotspots for high-priced homes, right? So right here, in what we see is Rancho Santa Fe and Solana Beach and Del Mar, and I'll be upfront that my San Diego geography is not excellent, so I'm just going to read what's on the map here. So these yellow spots, these look like they are probably concentrations of high values of homes. And out here in the desert, this looks like it's a big area of low values, but we want to be able to give some statistical certainty to those kinds of observations that we're making. So to get a handle of what's going on in our home value data, let's just go ahead and do a histogram. So we're centered around maybe $400,000. Right. And let's look at home value in quintiles. Again, this is basically the exact same data. We're just changing the classification scheme here. So something that gets highlighted here is this sort of what appears to be a cluster of low values down in Chula Vista. So lots of light colors together. There's lots of dark colors together. There's lots of heterogeneity happening in the middle here. So again, what we're going to try and do with exploratory spatial data analysis is try and use some statistics to describe these patterns that we see in the map and whether or not these are random, right? So if housing prices were random in San Diego County, this map would look more or less like a checkerboard, right? We would see light places in the same places that we see dark places. There would be no visual clustering of values in space. But and clearly in this map, we do see some of that clustering in space, but as Serge mentioned earlier, our eyes are drawn to the larger polygons. So we can't really tell if the clustering that we see in this map is going to be borne out by the stats. So that's what you see here, right? Our brains recognize patterns, but they're sort of drawn to the big areas of the map. So in PySAL, we have ways of trying to understand correlation in space, what we call spatial autocorrelation. So the way that we do that is to understand whether a focal unit shares values with its neighbors. And the way that we understand that is with the spatial weights matrix. So let's first look at this using a queen matrix. So we create a new queen weights object. We're going to row standardize it, which just means that your weight is proportional to the number of neighbors that you have. That way we don't let outliers really influence our spatial lag. So to understand relationships in space, we rely on this concept of the spatial lag. Right? And the spatial lag is basically the sum of the attribute values that are that share that are neighbors with our focal unit, right? So this is, once we row standardize, we look at the average value of the neighborhood around a focal unit. So for every census tract, we take its neighbors, we look at what the home prices are, and we take the average price of the homes in the neighbors of our focal unit, and that becomes our spatial lag. So let's see what this looks like in San Diego. We'll create a new variable called ylag, and that's the spatial lag using our queen weights matrix and the y variable, which here is the median home value in San Diego. And let's plot it. So unsurprisingly, this map looks a lot like our map of home prices. So the spatial lag of home prices looks very similar to the original map of home prices. And the way that the reason for that is that a spatial lag is basically a spatial smoother, right? So if we're calculating the average of a neighborhood and plotting the average of the neighborhood rather than just the unit itself, we're sort of smoothing the focal value around through its neighbors. So again, I think what you see in this map is that these patterns become even more lucid, right? So now we have this really obvious cluster of dark values here. We've got a pretty obvious cluster of light values down here, and some more light things going on out here, and then sort of odd things happening in the desert. Okay. Let's look at these maps side by side. So here's price, our original price data, and here's the spatial lag of price. Again, the map on the right is essentially a spatially smoothed version of the map on the left, where we see some of these local idiosyncrasies have been sort of massaged out through their neighbors. This gives you a sense of what the spatial lag is capturing. Right? But it's still difficult to say with certainty that we've got clusters here. So to ascertain that, we're going to use two different measures of spatial autocorrelation, and we'll start with join counts. So join counts are used often for categorical data. So we use this for trying to understand whether, say, trees of a certain genus tend to grow in the same locations of a forest, or whether census tracts that are above the median home price, in this case, tend to cluster together versus those that are below the median home price. So the terminology here is again taken from a chessboard where you have black cells and white cells, and you ask, unlike a checkerboard where they're randomly distributed, how often do we find black cells next to black cells and white cells versus next to white cells, and or this black-white relationship. So to do this with polygon data, we're going to start by discretizing our home price variable. So first we'll just grab the median, and then we're going to create a new variable called YB. And then we're going to use that YB to split the data set in half. So we've got a new variable that describes whether the home values in that tract are above the median or below the median. So in this case, dark values, the black cells here, are home prices that are above the regional or the county median. White cells are below the median. Again, we start to see some visual patterns here. All right, so immediately we want to know what's happening with these black and white areas. Is this statistically significant? So we've got 308 black polygons. How many times do we have a black census tract whose neighbors are primarily black, right? And how many of those would we expect if this were spatially random and distributed like a checkerboard? So to do that, we use the join counts function from ESDA. Right. So we create a new queen weights object. This is going to be binary contiguity here because these weights are the values are either 1 or 0, right? They're either white or black. And then we're going to create a new join count statistic. So that's going to count up the times that the neighbors in the weights object are the same as the focal unit, the times that they're different, and the times that are join. So black, black, white, white, and black, white exhaust all possibilities in our data frame. You have to be either black or white. So these are the only options that we have. You can see that we have 1927 observations in our data set, which is appropriate. And of those almost 2,000 observations, 736 of them are black-black joins. And so what we want to know with this statistic is if home prices were distributed throughout San Diego at random, then those above the median wouldn't necessarily be in the neighbor set of focal units above the median. If they're spatially random, then your neighbors should be above and below. So to do this, what we do is we basically shuffle the weights matrix hundreds and hundreds of times to create a synthetic distribution of space. And then we do the join count again, and we ask how often so we generate a distribution of join count values, and then we ask how often are the observed counts different from the distribution that we observe. So if you randomly shuffle the weights and you generate this distribution of black-black, which is above the median census tracts here, then you get a distribution that's roughly centered around, 475. And our statistic was 736. Yeah. So you can see, right, this is highly significant. This is way outside of our distribution of values under complete spatial randomness. And we can check the p-value because the pseudo p-values are automatically generated by this function, and we can see that sure enough, this is not spatially random. It is certainly true that tracts with home prices above the county median tend to cluster together. And that's interesting, but our home price variable is continuous. So we actually have a lot more data that we can take advantage of. So we don't have to discretize this in the first place. So let's take a look at spatial autocorrelation in the continuous case. So we're going to take our same queen weight object, and we're going to row standardize it again, because again, now we have continuous values and we want each neighbor in the neighbor set to count equally. So again, we'll create our Y value, which is the median home value in San Diego. And now we're going to calculate Moran's I. So Moran's I is a statistic that measures the correlation between a focal unit and its neighbors. So if you are highly correlated with your neighbors, in this case, the Moran's I statistic is 0.67, which is a pretty strong correlation. And if your values tend to be similar to those of your neighbors, we say there's high spatial autocorrelation in this data set. So again, similar to the join count where we just saw that black joins tend to cluster together. So neighborhoods above the median for home price tend to cluster together. Here, we're going to take the entire range of values and see if everything is correlated along the entire range of values. And so to look at this quickly, we can use this plot Moran function from splot. Splot is part of the visualization submodule in PySAL. And it's got a pretty simple signature. We give it our Moran's I object. We tell it that we wanted Z standardized, and we just give it a figure size. And what you see here is, again, we shuffle the neighbors, and we recalculate Moran's I, and we ask how often is the focal unit correlated with its neighbors under complete spatial randomness, and how does that distribution compare with the statistic that we observed. And once again, we see this tight distribution around 0, and our reference distribution and our measured statistic is way out here at 0.67. Right? So again, we have very strong evidence that we've got spatial autocorrelation in home prices in San Diego County. And the Moran scatter plot shows us this, right? So here we have home prices on the X, and we've got the spatial lag of home prices on the Y, and we can see how often these two values correlate in space, and Moran's I is the slope of this regression line here. Right? So the Moran's I basically calculates this slope of correlation between the lag and its the attribute and its lag. So in this case, again, very strong evidence. We've got spatial autocorrelation in home values. And again, we also provide a pseudo p-value. In this case, we've got very strong statistical evidence of spatial autocorrelation. So what that means is that if you're doing statistical analyses, like say a regression, and you don't account for the fact that values tend to cluster together in space, it means that your inference is likely maybe incorrect, right? Because you're not accounting for a really important feature of the data, which is local correlation. So what we just looked at above was what we call global autocorrelation. That's the degree of similarity across all observations between a focal unit and its neighbors. But we can also look at local autocorrelation, and this is defining hotspots and cold spots or outliers, right? Places where you have low prices surrounded by lots of high price neighbors, or places where you have a high price surrounded by lots of low price neighbors. So again, let's take a look at what this means. Again, we'll create, we're going to row standardize our queen weights matrix. We're going to create this object called lag price, which is just the spatial lag of home values in San Diego according to our queen matrix. And now we're going to call Moran local. And with the Moran local function of ESDA, we are generating Moran's I statistics for every single observation in our data set. So again, now, instead of a single eye that describes correlation among all the focal units and their neighbors in the data set, we have an array of eye statistics that describe the degree of relationship between a focal observation and its neighbors. Again, visualization is super, super useful in this context, right? So again, we're going to use a function from splot called Moran scatter plot. Again, and all we have to do is feed it our local Moran object. And what you see in the local Moran is this quadrant superimposed, right? And these define the median of each of the price and the median of the spatial lag of price. So these define basically 4 quadrants of high, high, low, 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 high, high, low. I always mix these two up, right? These are obvious. If you're in this quadrant, in quadrant 1, you're obviously high prices with high prices of your neighbors. And 2, you've got a high price in the focal unit, but a low price, a low price of the focal unit and a high price of its neighbors. Low price of focal unit and neighbors, high price of the focal unit, low price of the neighbors. And these we can use to define basically hot spots, cold spots, and spatial outliers. On a local Moran object, we've got this attribute called Q, which tells you what quadrant you are in the Lisa map. We sometimes call this a Lisa plot or a Moran scatter plot. Lisa is local indicators of spatial autocorrelation. And this gives us the quadrant that each observation falls into. So again, we can test for clustering. Each of the observations in our local Moran's eye has a p-value. So let's sum up all of those for which there is a significant I statistic. So in our data set, we got 241 observations whose local Moran's eye is statistically significant. And again, let's plot these. If you give a p argument to the Moran scatter plot function, it will shade the points that it shows according to their statistical significance. So here we're specifying a p-value of 0.05. And now, in addition to seeing what quadrant these points fall into, they're also shaded by their significance. So these are significant high hotspots. These are significant low hotspots here in orange. These are significant low-high. So these are low focal units surrounded by high lags. And we don't see any shaded dots down here in our high-low quadrant. Again, as I've described, high up here in the upper right, low, low, high. So again, visualization, super useful in this context. And splot gives us lots of really useful methods to plot these things quickly. Here we're going to do the Lisa cluster map, and we feed it our local Moran statistic, the San Diego data frame. We tell the significance that we'd like, and then the figure size. And now we've got our map, but in this case, the tracts are shaded according to their significance. So just as we thought, right, this area along the coast, these all shaded in red, this is a significant hotspot of high home prices surrounded by other high home prices. Right? The blues are low prices surrounded by other low prices. Those are scattered. There's a big area down here in the south, but then there's also little spots scattered throughout. It's difficult to see, but this light blue, these are areas of low prices surrounded by high price neighbors. So these are sometimes called donuts. These are sort of holes in the middle of something rich. And we don't see any high-low, which would be pink in this map. So there are no places where you have really high prices surrounded by lower prices. And again, this matches with our scatter plot that shows no colored dots here in the fourth quadrant. Okay, and so now that we've gone through all the hard ways to do this, there's another nice function in splot that will give you all of these visualizations at once, and it's called plot local autocorrelation. And despite the fact that this is at the end of this notebook, it's often a good idea to start with a function like this when doing exploratory spatial data analyses, because this gives you a really quick sense of how your variable clusters in space and whether or not that clustering is significant. So there are ways that you can extend this to multiple variable contexts, but I'll leave that for further exploration. And I guess now I'll stop for questions in case there are any. Yeah. People good with the pacing? There's no exercise in this case, so we'll save those for the next two. Okay. All right, great. Okay, I'll move on to the next one. Okay. So now let's talk about geodemographics. So geodemographics are a way of understanding, well, you can think of it as a way of understanding spatial autocorrelation among multiple variables, though it's not posited that way. But geodemographics is the study of people by where they live. And the rough way to describe this is that it's a cluster model applied to demographic data that you then plot. And so we assign, in this case, census tracts, because that's what's in our data set. We're going to look at the race and class values in our census tracts, and we're going to use a cluster model to sort them into a typology, essentially, a neighborhood typology, you could think of it as. And then we're going to plot that neighborhood typology on a map. And you can use that typology for guiding resource investment, or in the private sector, it's used a lot for marketing. And in urban planning, there's a push to use these sorts of things to develop better, more equitable, affordable housing plans, and like I said, target resources a bit more efficiently. So I'll show you a bit about how this works and how it could be extended into the future. Okay. So in this case, we're going to use a bunch of stuff from PySAL, but we're also going to use some functions from our friends over at scikit-learn to do the clustering. I'll just give a small plug again. It's useful to walk through this stuff manually in this notebook, but again, over at CGS at UCR, we're developing another package called Geosnap that wraps up a lot of this functionality into a slightly easier to use API. So if you are interested in this kind of analysis, I encourage you to go check out Geosnap, which will do the same kinds of work, but with a little bit less code. Okay, so again, we're just importing GeoPandas, some of our friends from Scikit, and then some interactive plotting, because it's a lot easier to understand these things with an interactive base map. Again, we're just going to load the Southern California region. We're going to fill any NA values with 0. Make sure our plot looks correct.
I think you got to share screen.
Oh no. Sorry, folks. How about now? Okay. So our imports are just scikit-learn, PySAL, GeoPandas, some interactive viz. And let's take a look at our data set. Again, we're relatively familiar with the Southern California region at this point in the workshop. And this time, let's just look at LA. So we're going to grab from our SCAG data frame where the first 5 characters of the FIPS code are 06037, which is Los Angeles. We'll create a queen weights data frame, a queen weights object from the data frame. And then we're going to get rid of the channel islands. So as Serge mentioned, this concept of connected components, just to make our visualization a little bit easier, we're going to drop these islands that are normally part of the LA County, and we're going to use a PySAL weights object to do that. So when we create these queen weights, we've got one component, which is Los Angeles, and a second component, which is the channel islands, because these are multi-polygon. And by specifying that we want to select from our LA geodata frame where the indices are drawn from the first component, which, because Python is indexed to 0, we're grabbing only the tracts that are part of mainland LA and not the channel islands. So that's a nice quick way of subsetting to get rid of stuff on the periphery. And this looks how we want it to look. So I didn't run this cell. There we go. Island's gone. Okay, so as I mentioned before, this link will take you to a little bit of background on geodemographic segmentation. But the general idea is that it's unsupervised clustering applied to typically demographic and socioeconomic data, though sometimes in the private sector it also includes behavioral data and purchase data. So there are vendors like, I'm blanking at the moment. There are lots of vendors. Experian puts together a geodemographic typology and it sells it to retailers and other vendors all throughout the world. Esri has its own geodemographic product. Advertisers have recognized that this is a really useful way of summarizing data that is predictive of people's behavior. And that has to do a lot with the way that people decide to segregate themselves either by race or class, and then once they're segregated, they tend to behave in similar ways. And so we're just going to take a look at how we would try and understand the region according to a handful of variables that correspond loosely to race and class. So we're going to look at household incomes, home values, and then racial categories: white, black, Hispanic, and Asian. Okay. So we're going to start by creating a new variable that holds our columns. And because we're going to do a cluster, it's useful to scale our inputs so that we're not getting influenced by one particular variable over another or by outliers. So we create a new standard scalar object from scikit-learn. And we're going to create a new k-means cluster object that we call LA k-means. And we're just going to look for, in this case, we're just going to pick a number out of our hat. Let's find 6 clusters in Los Angeles using these variables. And all we care about are the labels at this point. We're going to introspect later how well this model fits, but right now let's just take a look at the labels. And that cluster object has an attribute called labels underscore that contain the integer labels of the clusters that we found. Now let's just assign those labels back to our data frame in a new variable called k-means. And let's plot that to see what it looks like. Okay. So right away, you start to pick out some visual patterns. Right out here, you have this big continuous block of purple. If I zoom in a little bit, we've got this big contiguous block of blue, and this little green here in the middle. There's this sliver of pink inside this sort of turquoise color. We've got more of this purple along the coast here. And so as with the spatial autocorrelation notebook before, right away we can visually start picking out some patterns here. And this is how the Los Angeles region divides itself according to race and class. If you know Los Angeles well, you can probably start guessing what some of these clusters might mean. But if you don't know Los Angeles very well, it's a good idea to try and understand what each category represents. So let's just do a quick group by on our k-means labels and look at the average values inside each one. So it's kind of difficult to grok this quickly because these aren't fixed width columns, but we can see that there is quite a bit of variation in the white population and the black population, slightly less so in the Hispanic population, quite a bit in Asian and median income, right? So cluster 1, for example, is nearly 50% Asian. Let's look at where cluster 1 is. We should have put a legend on this map. 1 is the green color. Cluster here, cluster here. Okay. But it's hard to take in this table all at once, right? If you isolate a single variable at once, if you isolate a column and try and look for, say, the largest value, that's a good way of, say, picking each one. But what we want to know is sort of how these values differ across the range of input variables and across the clusters themselves. So I like to use violin plots as a way of trying to understand what's happening here. So here we're just going to use Seaborn and loop over all of the columns that we care about and create a violin plot. And these are basically just a kernel density distribution rotated on its side. And so we've got the box plot superimposed over the distribution for each variable. And these are a really good way of trying to understand how the clusters differentiate from one another. Ideally, the clusters here are the cluster values here on the X and the value of the variables on the Y. And what we want to understand here is how much vertical separation there is between these different distributions. Ideally, as we move through the different clusters, we want there to be a good amount of separation here so that we know that we've got a good, solid, well-defined cluster. And if we look at these maps, we look at these plots, we start to see that some of these variables are better at differentiating clusters from one another. Right? So again, cluster 2 is far and away the largest Asian population because this distribution is often doesn't even overlap with these others. Right? The same is true of the black population. It's highly clustered in cluster 5. Median home value is highest in cluster 1, which is the same. The same is true of the household incomes, again, like we might expect. Because we know something about the correlation of race and class, that also happens to be the neighborhood type with the largest share of white residents. So cluster 1 is arguably sort of a cluster of privilege, of neighborhoods with high home values and high incomes that white folks have largely been able to exclude others from, given the fact that they tend to be 75% white on average. Right? But even though these violin plots help us understand the clusters, this is still a sort of visual inspection. We still want to understand if there's some statistical measure of fit in how well this typology has been created. So to do that, we're going to use a silhouette score, and the silhouette score basically tells us how well our clusters differentiate from one another. There's, if you want to learn more, please check out the scikit-learn documentation, which is fantastic. So we import the function from scikit-learn, and we just give it our input data and the labels of our output. And so it gives us a silhouette score of 0.32, which is not too bad. But we just picked a clustering algorithm out of the hat, and we picked a value for K out of the hat. So clustering algorithms use different approaches to try and understand how values cluster together. And your choice of the number of clusters has a really big influence on the fit. So we can also look at how our solution would change if we use a different algorithm or if we use a different number of K. So let's test out affinity propagation, which is a pretty new clustering algorithm. And it takes these two parameters, damping and preference. And just through some of my own exploration, I found that these two tuning parameters tend to work well. So that's what we're going to use here. But that's by no means scientific, so we'll have to test that a bit later. And affinity propagation is a bit more computationally intensive than k-means. So this cell takes a bit longer to run, but now it's finished. And again, it gives us this attribute called labels underscore that holds the labels for our discovered types. And in this case, our silhouette score is slightly higher. So we've got a little bit better fit using affinity propagation than when using k-means. One thing about affinity propagation is that the number of clusters is endogenous. So we give it these two parameters and it comes back with course. Okay, after a series of typos, we can see that there are 5 unique clusters using affinity propagation with these tuning parameters. So one fewer than our k-means model. We will attach these labels back to our data frame so that we can compare both solutions side by side. And this is something that's nice about hollow views. We use this little plus operator to do 2 plots, and it will lay them out side by side. So let's take a little bit to generate. And the nice thing about using hollow views to do these is that the plots are linked so that as we scroll on one, we're going to scroll on the other. And this helps us understand whether we're picking out basically the same clusters and whether they share the same space. Now, the cluster label and the color aren't comparable between the two plots, but the prevailing spatial pattern is comparable, right? So in this case, at least down in Inglewood, much of the patterns discovered by both clustering algorithms is quite similar. I think that's true for much of the region. Indeed, we end up with similar patterns. So this is interesting, right? We're taking a look at, 5 variables, 6 variables, race, class, it's pretty parsimonious. But right away, when we start plotting the values or the labels of these clusters, intuitively, we can pretty obviously pick out spatial autocorrelation, and that tells us that the underlying variables tend to be spatially autocorrelated. But we're just allowing that to fall out, right? The space is not accounted for in any way in this analysis. We're simply creating a cluster model and then plotting the results of that model on a map. The spatial clustering just sort of falls out from the underlying data. As an alternative, we can use spatial weights matrices as part of the clustering process to ask for regions of our study area that are both similar in attributes and share a approximate relationship, right? So if we're using queen weights and we do a spatially constrained geodemographic, what's often called regionalization, then we're going to end up with clusters of values that are the same and also share a vertex or an edge. And this is useful when you're trying to find out, rather than just a typology of neighborhoods, regardless of where they are, which is how the general clustering process works. With regionalization, we're asking how to distinguish contiguous parts of our study area according to their underlying variables. So again, we'll create a W object using queen weights. And scikit-learn is pretty nifty in that it can just take a PySAL weights object as part of the clustering method. And this is unconstrained. So here we're looking at hierarchical clustering in scikit-learn. I'm looking for eight different clusters, right? K equals 8. So this is exactly like what we were doing above with k-means and affinity propagation, only here we're upping the number of clusters to 8. And I don't like that plot because don't feel like playing with this plot, and I know that if I change set the right Seaborn style, it will automatically change my line widths, but that's fine. So here we're doing a hierarchical agglomerative cluster. We're not constraining it in space, so you can see that the values are allowed to be anywhere. But scikit-learn has this nifty connectivity object, connectivity argument for agglomerative clustering that we can feed a PySAL weights object to. So here we give it the sparse representation of our W, and we ask for exactly the same cluster model. We're going to use word linkage with 8 clusters with the exact same data, only this time we're going to constrain the clustering so that observations can only be grouped together if they're also neighbors in our queen W. Again, we'll create a new column called ward spatial, and then let's plot both maps side by side. All right. So again, these are using the same algorithm, the same input data, the same number of clusters. But the patterns that they find are obviously quite a bit different because this one is enforcing queen contiguity, whereas this one is not. Right? We end up with some similar patterns. Right? We still get sort of this cluster of orange or gray here in the west. We still get, well, a lot of the same happening up in the less populated parts. We still get some of the same racial patterns that we get in Inglewood and in South Central LA. So this turquoise color. But otherwise, these look quite different. And here we're identifying spatialized communities that are sort of both relatively homogeneous on their attributes and are together in space. Again, we can take a look at how well these models fit. So the silhouette score of our collaborative clustering model isn't quite as good as our k-means or affinity propagation was. And it's much worse for our spatially constrained solution. So I will stop there and ask whether anybody wants to venture a guess for why our silhouette is so much higher for the unconstrained versus the constrained. And then we'll leave it for some exercises here at the end. Hello. Anybody want to venture a guess why our silhouette is so much lower? So Zafar, with affinity propagation, the classes are endogenous. They are dependent on those two tuning parameters, damping and preference. And if we change those, affinity propagation will return its interpretation of the best fitting cluster model where K can be really high. Affinity propagation has a tendency to create a lot of clusters. And if there are so many clusters, then it's not a very good summarization of the data. The whole reason that we want these clusters to begin with is because they help us summarize what are thousands of observations. And so if we end up with hundreds of clusters, that doesn't help us intuit much faster. Yep, Stephen's right. All right, so the silhouette score is examining how well the values in one cluster are similar to one another versus being similar to a different cluster. If we're constraining those to be in space, you can't choose to be in your next best fit cluster because you're not allowed to. So by definition, we're going to get a less, our model fit is not going to be nearly as good because there's one additional constraint on it. All right, so we'll give you a couple minutes to do these exercises. Until about 10:20. Take a couple questions. Otherwise, so far, so good. Pacing okay? It really is like you're flying blind when you're presenting. You really have no idea what's happening. Good question. I'll cheat and show you. It's 06059. So Dan, there's also a brand new concept of a geo-silhouette, which I didn't cover. And it's going to be a resource here in a second. That is a paper that describes a geo-silhouette which attempts to apply this logic to clusters in space. Let's take a look at some of the results here. Okay, so first we want to pull out the Orange County data. Then we create two different cluster models. One using k equal to 5, one using k equal to 8. I'm using that same scalar object, which gives us z-scored observations here. And then we just calculate silhouette scores for both groups and take a look at what the results are. To find out the average home price in cluster 3, we first pull out the Riverside subset, so county 065. We create a new affinity propagation cluster model, and all we care about is the labels in this case. So we've attached those as a new column called affinity propagation. Then we just need to grab the unique labels from that column. And then if we do a group by object, we group by that new variable and grab the mean. Then all we care about is cluster 3. That'll give us the average home price in cluster 3. So the 5 cluster solution was a little better. We find 6 clusters in Riverside with an average home price of 176,000. And if you think about what would happen with distance-based weights, right? With distance-based weights, you are still neighbors as long as you're within some threshold, even if you don't satisfy edge or vertex connectivity. So what that means is if we use distance band weights, we are not guaranteed to find these geographically contiguous and tight clusters. The result will still be spatially influenced, right? Because you still have to be within a neighbor set, but the clusters won't be as well defined in space since contiguity isn't strictly enforced. All right. So if it wasn't clear from the last notebook, race and class are powerful dividing lines in space. People tend to select into neighborhoods with folks that are similar to them in race and ethnicity and income. And when you build geodemographic typologies, it's really easy to visualize some of those characteristics. But there's also a massive literature on segregation and how you measure it, and the different kinds of segregation that can arise from different dimensions of people sorting into space, right? So whether it's unevenness or centrality or clustering, right? Segregation has these different dimensions. What's always been sort of a major challenge in segregation work is comparing one place to another or comparing a place to itself over time. So at CGS, we've been developing some new ways of trying to understand that, and we're going to walk through a little bit of that in this notebook. Again, just a little bit of boilerplate. Here we're going to use the segregation module from PySAL, GeoPandas. We're going to use our same, what I'm going to do is click all the outputs. We're going to use our same data. So we read in Southern California data set. Here we're going to reproject it to UTM-11. So our units are in meters. Okay, and we're going to look at Hispanic, non-Hispanic segregation in Southern California. So we're going to drop any observations that have missing data and plot them. So this is how the Hispanic population is distributed throughout the region. Large hotspots in Los Angeles and in Riverside. So some in Ventura. And also large concentrations in some of the rural areas, like out here in eastern Riverside County. And because we've been fighting with FIPS codes for the last 3 hours, this time let's try something a little bit different. So we're going to create a new variable called county that just holds those first five characters of the FIPS code. And here are our unique counties in the region, and those correspond to these county names. And instead of trying to looking up each time we try to do an analysis, let's just rename this variable to have the name instead of the FIPS code. So we create a new dictionary that zips together the code and its name, and then we use that dictionary to replace county names in our GeoData frame. Now this is going to be easier for us to parse and easier for us to select by, because we've got a more recognizable feature there. And now let's split the data set into the coastal and inland regions. So the coast is defined by the counties LA and Orange, San Diego, Ventura, and inland, where UCR and our university is, those include Riverside, San Bernardino, and Imperial. Okay. So here are the counties along the coast, colored by their county name. And here are the inland counties, right? These fit in right here. And what we want to know is, does segregation in Southern California differ between these two regions? There's a lot of disparity between the coastal and inland regions. And we want to know, is there also a lot of racial disparity in terms of who shares a neighborhood? So now we've got our two regions set up. Let's take a look at different segregation measures. So depending on what tradition you come from and which literature you ascribe to, you may have a favorite segregation index. The PySAL segregation module calculates over 40 of them. So we don't take a position on whether one is preferable to another. These different segregation statistics have different useful features. And so we want to provide the menu of all of them available to folks in whatever field they may be. So let's just take a look at 3 different indices: the dissimilarity index, the Gini index, and the entropy index, and use them to calculate Hispanic segregation in these 2 regions. Now, these are non-spatial indices, so they don't account for space. We're only measuring the population in the focal unit itself. And I called these single group indices, but that's not really appropriate, right? These are two group indices as opposed to multi-group indices. So here we're measuring Hispanic versus everyone else segregation. Sometimes you might want to isolate that to, say, Hispanic versus the non-Hispanic white population to try and understand different aspects of racial or ethnic segregation. But here we're saying, how is the Hispanic population segregated from everyone else? Okay. And each index in the PySAL segregation module is implemented as a class. So that class takes an input data frame and the name of the column containing the sort of the focal group, and the name of the column containing the everyone else group. So I said in this case that the everyone else is the entire population, but sometimes you want to tweak that a little bit. And each class has an attribute called statistic that gives you the measured statistic for that particular index. And as we can see, there's quite a bit of variation in these statistics. They range from 0.24 to 0.48, but they are measuring quite different things. So the fact that these are different doesn't tell us much, right? These aren't necessarily comparable across different statistics. There's also multi-group indices. So here we can give different population groups. Here, let's look at the same groups that we used in the geodemographic typology. So we'll look at white, black, Asian, Hispanic. And here we'll calculate a diversity and a multi-information theory index. The multi-information theory is basically just an extension of the entropy index. And again, different units, different values. How do we make sense of these things? The point in this part is how quick and easy it is to calculate a wide variety of statistics using some simple input data and just the PySAL segregation module. You can really quickly generate any of the 40 plus indices that you think are appropriate. But as we talked about before, these indices are ignorant to the concept of space, right? They measure whether people who share the same tract are different from one another. But tracts are a political construction that don't necessarily have any intuitive meaning to people. I mean, if I asked anyone in this tutorial what census tract you live in, I'd be really surprised if any of you could tell me. I do this work on a daily basis. I certainly don't know what census tract I live in, and you don't know where the boundaries are that define one from another. So using an arbitrarily chosen polygon like a census tract as your measure of who's in a neighborhood together can affect the statistic that you're trying to measure, but it also is not necessarily a theoretically coherent object, right? A census tract is just a unit of convenience because that's how our data come. When we use a spatial index, we have much more control over the concept of space and how much it matters. So we'll take a look at how we can use different sorts of weights objects to create different versions of these statistics. Again, we'll just use the dissimilarity and the spatial information theory index. And we're going to create two different weights objects, right? So one is a queen, and another is a distance-based weights, distance band weights. Remember, our coordinate system is in meters. So here we're asking for neighborhoods that are up to 2.5 kilometers. Now, a neighborhood being 2.5 kilometers may sound quite large, but we can play with this number and dial it up or down to see how the size of a neighborhood influences our statistic, right? Again, remember what lags do is sort of spatially smooth the data. So this is sort of like saying, what's the bandwidth over which we want to smooth this neighborhood, and how do we account a distance decay for more distant units? So we'll start with a single group statistic. Let's just calculate the spatial dissimilarity for Hispanic persons using queen contiguity. And you notice that these are going to take a little bit because our distance band weights takes a little bit of time to calculate. And there we go. We've got a spatial dissimilarity statistic of 0.353. We need to do dissimilarity up here. All right. So this describes spatial dissimilarity using a Queen's matrix. Let's also take a look at this. This time, the other weights object. And we can see already that the way that we define space is going to influence the value of our resulting statistic. Now, that doesn't look like it's a huge change, 0.35 to 0.33. But it is a change, and so that tells us right away that the way that we conceptualize space is going to have an effect on our resulting statistic. And so we can also extend this to the multi-group case. So again, we're just passing a data frame, our population groups, which correspond to columns on the data frame, and our two different concepts of spatial relationships. Again, different, not wildly different, but different enough to care, right? Because if you are conceptualizing space in an incoherent way, say using distance bands that don't account for the curvature of the Earth, you're wrong on two fronts. Right? You haven't captured spatial relationships well, and your index is going to be biased because of the way that you've defined space. Okay, so we've seen that the way that you define space matters. And some folks have already thought about this in terms of the scale of geographic segregation. So you can think about neighborhoods, places that are micro-segregated, where they may look like a checkerboard, right? Let's say you have black neighborhoods and white neighborhoods, 90% and 10%, right? But they are mixed in together. The neighborhoods that are predominantly black, say, are 90% black, but they're next to a neighborhood that's 90% white, and it's next to another neighborhood of 90% black, right? And you can imagine like a checkerboard pattern, right? Each of the individual units can be highly segregated, but if you look across the whole region, that doesn't look like there's much segregation, because if you average it out, it's hard to tell. Conversely, you can have places where people of different races or ethnicities share completely different regions of the study area. So to give you two examples, New Orleans is a good example of micro-segregation. It's got lots of highly segregated neighborhoods that are in close proximity to one another, versus, say, Washington, D.C., where I'm from. If you plot the black or white population in Washington, D.C., you'll see that D.C. splits essentially right down the middle, right? That there's not these intermingling of highly segregated small neighborhoods. It's one half of DC is very different from the other half of DC. So that's describing micro scale segregation versus macro scale segregation. And if we use a multi-scalar profile, essentially what we do is calculate a segregation statistic at different spatial scales. So we take a distance band or a kernel weight, and we give it a range of distances, and we calculate a new segregation statistic at each range. And I'll let this run because it actually takes a minute. And what this will do is generate a list of values that, if you sort of plot them, you can understand the shape of the segregation curve relative to distance. And we'll see what that means here in a second. Hopefully you can run these. I'm not sure if sometimes Binder is a little finicky if you haven't been on it persistently the whole time, so I hope nobody's Binder instance has crapped out. And as you can see, this is kind of computationally intensive. I think this cell still runs in like 30 seconds or so on Binder, but on my relatively powerful but kind of old MacBook, you can see it takes a while. The reason it does this is because it has to generate a new weights object for each distance and recalculate the resulting statistic. So the segregation module has this function called compute segregation profile. It takes a data set, it takes a set of distances, and right now it calculates the multi-information index. Soon we'll generalize this to be able to calculate other kinds of segregation indices, but the segregation profile was originally defined on the multi-information index. So this is a slope of the segregation profile in Southern California for Hispanic, non-Hispanic segregation. And what this shows is that the further you travel over space, the lower that segregation falls, right? So by assessing the slope of this line, we get a sense of how macro versus micro a region is segregated. A steeply sloped line indicates that most of the segregation is at the micro scale because it falls quickly, versus a flat segregation profile indicates that a lot of the segregation still remains at larger spatial scales. So this could be a nice way of comparing places to one another and comparing the scale to one another. And this is useful, particularly in our context, looking at Southern California, because of the different land use contexts. The coastal region is a lot more urban and a lot denser. The inland region where we are is a lot more rural and has some really large tracts out in the desert. So depending on how you parameterize the weights, that can have a big impact. I should have been running these while I was talking, because these are also going to take a little bit of time. But here we're going to calculate the same segregation profile, but we're going to do it for the two regions that we defined earlier, the inland region and the coastal region. This one, and this one. And then when they're finished, we'll plot those segregation profiles on the same graph and see whether, one, whether one line is higher than another, and two, whether their slopes cross, whether they have similar slopes, whether one region has greater segregation at every scale versus only at some scales, and so forth. And this is probably the longest running cell in the entire workshop. While this runs, I guess I'll drop into questions just in case. So the Y is the segregation statistic, and the X is the distance from the distance weights. Okay, we're getting there. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. So we plotted all three values, all three profiles on the same plot here. So the blue line is all of Southern California, the entire region. Orange here is the coastal region, and green is the inland region. Right away, we can see that much of the segregation in Southern California is driven by the coastal region. The segregation profiles are very similarly shaped, but the coastal region is so much higher than the inland region at every single spatial scale. So 0 is the spatial version, right? This is at only the tract level, versus as we start increasing our distance moving out. So as we account for more macro levels of segregation, how does it change? And as I said, the coastal levels are so much higher than the inland levels at every scale. Okay, so that is pretty interesting. But what we'd like to know is, visually this looks like quite a big difference, but that has a lot to do with the way that the units on our axis are chosen, which we didn't set. So this may be a small difference if we look at sort of the distribution of differences in the region, and we have no idea. Certainly this looks like it's quite a ways away. So to try and understand that, there is an inference framework that's part of the PySAL segregation module. And to use it, we import the single value test from the inference module. And this tells us whether our segregation statistic is significantly different from what we would observe under complete spatial randomness. And similar to the local autocorrelation test, we get p-values. And you're looking at our simulated distribution of the statistic here, really tight distribution at 0, versus our observed statistic, which is 0.25. So the entropy, both the entropy and the dissimilarity statistics are statistically significant in Southern California. These are regions that are way more segregated than we would expect to be given their population composition. And we can also ask, how do two values compare with one another? Is segregation in the inland region significantly lower than that in the coastal region? And for that, we use the two-value test. And we give it two indices. In this case, we'll test the multi-information theory. So we're going to look at the difference between the information index in the coast versus the information index in the inland region. Again, this uses a permutation-based approach. And we wrote the code a little bit more recently, so now we included these fancy progress bars. Right? And again, we can look at the estimated point difference, which in this case is quite a bit and is significant. So the difference, this difference that we observe here at the 0 scale, so technically we were computing this difference, is statistically significant. The coastal region is significantly more segregated than the inland region, according to the multi-information statistic. Okay, and then finally, we have this brand new decomposition framework. And the idea here is that we would like to know, we've got two different segregation measures, one for the inland region, one for the coastal region. But those two regions differ in two important ways. They have different population compositions, and they have a very different makeup of their census tracts, right? So if we look back at these maps, right, the inland region has some of these giant census tracts way out in the rural areas, and then there's the places that are more urban in the inland region still have a lot of heterogeneity, where there's lots of tiny tracts surrounded by big ones, and this implies a certain spatial relationship that may not be the same in the denser, more urban regions. Right? So again, look at the relationships. Look at how many more neighbors, say, these dense tracts are going to have than some of these large ones. So there's two things that vary when we're comparing segregation inland versus coastal: their population makeup and the configuration of their spatial units. And we want to know which of those is the greater contributor to the difference that we see between the two regions. And that's what the decomposition framework in the PySAL segregation module tries to capture. The way that we do that is to basically simulate how the regions would look if they swapped population compositions. I won't get into the detail, but we basically use the cumulative distribution function to imagine what it would be like if one region were laid out like the other, and or had the population composition of the other place. So to use the decomposition framework, we have got a class called decompose segregation. We need to provide it with two statistics. Here we'll do the spatial dissimilarity. So we're doing non-Hispanic Black segregation according to the spatial dissimilarity statistic in the coastal and inland regions. And what we see here, the CDFs here are plotting the composition of the Black population. And the way to interpret these is that in absolute value, you want to understand which of these numbers is bigger. So if you see a sign in here, you ignore it. And in this case, we can see that in large part, the difference between the inland and coastal regions has to do with their different population makeup rather than the configuration of their census tracts. So if we were to swap the coastal population into the inland region, we would probably get segregation statistics that look very similar inland as they do for the coast. All right. And we've got just a few minutes left for an exercise. And with that, I will turn it to you guys.
We could do the exercise, or maybe if there's general questions, have a discussion for things we didn't cover, or it's a long time for people to sit and listen to us. So
Yeah.
I mean, we've tried to answer the questions in the chat, but you can only ask so much in there.
So just so that you can see it, I will show you the results. It turns out here are the statistics for each county in the region. So it looks like LA is the most segregated county in the region. Ventura is more segregated than Riverside. And the difference is primarily due to population composition. So we've got 5 minutes left. If anybody has any questions or something I didn't describe well, or anything at all you want to ask, please feel free.
We should point out that maybe we said at the beginning, but it's been a couple hours. So we're part of the broader PySAL team. So a lot of the stuff we've done is the stuff we're directly involved with, but there's a broader library, about 16 packages that we didn't cover today. So there's more to do with PySAL. There is the book coming out well, it's online now. We're doing a Jupyter book on spatial data science with PySAL. So please see that. The link's somewhere in the chat. We also want to thank our funding sources. NSF has funded a lot of this work. So we are computational social scientists. We have grants to work on these new segregation measures, scalable geospatial analytics that comes from NSF. And the idea is to turn this into production quality code that other domain scientists can use. So we're very appreciative of that funding. And then finally, all our compadres in the Pythonista world, we would not be able to do any of this without the SciPy, NumPys, GeoPandas of the world.
Yeah.
We will certainly accept with geospatial backgrounds. Yeah, earth scientists. Yeah. There's excellent packages already in there. So we don't want to duplicate, but I think there's interesting areas for synergies between what's going on with, say, Pangeo, what's going on with coupled natural human systems. And I think starting to have those dialogues would be fantastic.
Yeah. In the past, we have just simply not had a lot of overlap because some of the methods that we use are different. Some of the data formats are different, right? So natural science tends to skew a little bit more toward the raster side. But that's not because we don't want to collaborate. It's because, everybody sort of tends to play with their own toys. We would definitely love more overlap with the earth science world.
And we do have 3 Google Summer Code projects going on right now. One of them is to extend raster functionality in PySAL. And we also have monthly developer meetings on the first Friday of every month, and we're growing the group, and people from all backgrounds, all levels of interest and expertise are welcome to join. Everything's spatial in our view, so.
Jennifer, I don't think we're going to do a Geosnap sprint this year. Just because of the way that the formatting has worked out, and none of the other developers are around, and we've still got more to our day once we're done with this tutorial. But we can set one up if you want to participate, because I know it was really useful to have you around last year. So maybe if anybody else wants to join us for a code sprint, we'll find a way to make that public. And Mark, PySAL is completely coordinate system indifferent, agnostic. It doesn't you can use it anywhere in the world as long as you've got basically a CRS. Your measures are going to be valid. Hassan, if you go to PySAL.org or the PySAL page on GitHub, so github.com/PySAL, those are the best ways to get in touch with us.
Yeah, there's a Gitter. Put the link in there. Everybody's in there, so that's one way to get connected.
Otherwise, we have our own websites and Twitters, and feel free to reach out to us individually.
All right, well, thank you all for participating. It would have been much better to be there, see you physically and interact that way, but hopefully this was still productive for everybody. I think we had a good time.
Moderator, do you know what our maximum attendance got up to?
Yes, we got up to 221 people for most of the session.
Great.
Amazing. So thank you both so much. There's lots of appreciation in the chat, so I encourage you to go back and read that as well. As soon as this broadcast ends, you will be able to revisit this tutorial under the same link, so feel free to do that. Thank you, Serge, and thank you, Eli, for your time today. We will now end the broadcast.
Thanks for having us, folks. Thanks for being here.
Thanks.
Bye.